Pandas is one of the most popular Python libraries, and in the next 4 hours I will show you how to use it as a pro. My name is Martin Yanev and I am a software engineer and a computer science professor at Fitchburg State University. And in this course I will show you how to use the most powerful Python library Pandas for input-output operations, algorithms for arithmetic, aggregation, visualizations with matplotlib, data handling, and many more. Watch this course until the end and follow all the principles that I'm going to cover in the next 4 hours, because they will improve your Python skills by a factor of 10. After the end of the course, you will be able to handle datasets in Python like a pro. I will show you all the necessary techniques. If you feel that you get a value from this free tutorial, please make sure that you subscribe to my channel and like this video. And now let's jump straight to the course.
Selection from a pandas series involves accessing elements either by their position or by their label. Today, we will dive deep into understanding how we can effectively use selection in pandas series. Think of pandas series as a special kind of list, where we can not only access elements by their index, but also manipulate and interact with data in a way that is both powerful and efficient. Now let's see how we can implement a pandas series to illustrate its structure and functionality. We begin by importing the pandas library, a crucial step in utilizing its powerful data manipulation capabilities. Next, we create a series by passing a list of integers 10, 20, 30, 40, and 50 to the PD_Series function, while also specifying custom indices for each value using the index parameter. In this example, the indices are labeled B, C, and E, allowing us to access these values using more intuitive identifiers rather than standard integer positions. After creating the series, we use the print function to display it. This will show our data in a tidy format where each integer is aligned with its respective label. By doing so, we not only create a simple data structure but also allow ourselves to quickly reference each element by its label throughout our data analysis journey, enhancing both code readability and ease of data manipulation in future tasks. Let's explore how to extract a specific value from a pandas series using its label. We will start by writing a line of code to assign the value linked to the label C to a new variable named valueC. This process involves indexing our data series with the label C, showcasing the straightforward and readable nature of pandas. Once we execute this code, we will print the value of valueC, and we should see the integer associated with C, which is 30. This method demonstrates the intuitive way of accessing elements in a pandas series through labels instead of positional indices. The clarity of this code not only improves readability, but also maintains efficiency, particularly when dealing with larger datasets. By retrieving specific entries via their labels, we gain a significant advantage over numerical indexing. This approach is essential for effective data manipulation, allowing us to retrieve and utilize specific data points with ease. We can use the iloc method to implement integer-based selection in our pandas series. In this instance, we assign the first element of our series to a variable called firstValue by accessing it via data iloc0. The iloc method is particularly advantageous for retrieving elements based purely on their positional index, which starts from 0. Consequently, iloc refers to the first position in the series. Once we have retrieved the first value, we print it to the console using the print function. Executing this code will show the value linked to the first label, which in this example is 10. This selection technique is particularly useful when dealing with large datasets, as it facilitates fast access to specific elements without needing to reference their labels. Learning to use iloc effectively significantly improves your capability to navigate your data with enhanced flexibility and efficiency. Now let's take a look at how we can easily retrieve multiple items from our series using their labels. We can achieve this by passing a list of the desired labels to the series. For instance, when we write subset labels equals data B, C, D, we're extracting the values associated with labels B, C, and which gives us a concise view of the selected data. The output showcases these labels alongside their corresponding values, reinforcing the intuitive pairing of labels with their respective data points. Next, we'll see how we can implement a similar functionality using positional indices. By utilizing the iloc method, we can access elements by their integer positions. In this case, subset indices equals data iloc1, 2, 3 allows us to select the second through fourth elements, namely those associated with the labels B, C, and D again. This demonstrates how both label-based and index-based selection can yield the same results, providing us with flexibility in how we access our data. By mastering these techniques, we can streamline our data analysis processes efficiently. Now let's see how we can slice our series to obtain a range of items by their labels. When we use the syntax data BD, we effectively ask pandas to provide all the elements from label B to labeled inclusive. This inclusive nature of slicing in pandas makes it particularly user-friendly, as you don't have to worry about excluding the end label. After executing this line upon printing slice data, we will see the output displaying the values associated with labels B, C, and. Next, we will write the following code to achieve the same outcome using integer-based indexing. By utilizing the iloc method with the command data, iloc14, we access the positions corresponding to those labels, specifically from index 1 to index 3. Just like the previous method, this code yields the same set of values, 20, 30, and 40. This dual approach to selection reinforces the flexibility and power of pandas, enabling you to switch effortlessly between label-based and position-based indexing according to your specific needs. Let's explore how to check for the presence of a specific label in a pandas series. We can utilize the in keyword, which allows us to efficiently determine whether a label such as Z is included in the series. By incorporating this logic into an if-else statement, we can adjust the program's behavior according to whether the label is found or not. If the label Z is detected in the series, the program will display a message confirming its existence. However, given that we know Z is not a part of our series, the code will execute the else clause, resulting in a message that acknowledges the absence of the label. This method not only helps prevent key errors that might interfere with data analysis, but also exemplifies an essential coding best practice, verifying assumptions prior to accessing data points. Consequently, checking for the existence of labels is crucial for ensuring robust and error-free data manipulation processes. Now let's see how we can implement filtering in a pandas series based on a specific condition. In this example, we are creating a Boolean mask by applying a condition to the series, specifically filtering for elements greater than 25. The expression data 25 generates a Boolean array where each element's value indicates whether it meets the condition. This mask is then used to select only those elements from the original series that satisfy the condition. The result is a new series, filtered series, that consists solely of the elements whose values exceed 25. This is a powerful feature of pandas that allows for efficient data manipulation and analysis. Running this code will produce a filtered result that retains only the relevant elements, demonstrating how easy it is to sift through data based on conditional logic. The ability to filter data in this manner is essential for effective data analysis, paving the way for deeper insights and refined datasets that can then be used for further exploration. Now let's implement the following code to reset the index of our filtered series. The resetIndex method is a powerful tool that allows us to refresh our series, particularly after we've filtered or transformed the data in any way. In this case, we are using it on filtered series, which contains only the values greater than 25. By employing the parameter drop equals true, we instruct pandas to discard the old index instead of adding it as a new column in our output. This is essential for maintaining simplicity and clarity in our data manipulations. After executing this line of code, we can print out the new series, which now features a clean default integer index starting from 0. This transformation ensures that the series is easier to work with and provides a more straightforward frame of reference, especially when drawing further insights or performing additional operations. Resetting the index helps eliminate confusion that might stem from previous index labels lingering from earlier data states, thus enhancing our data processing workflow. Now let's take a look at how we can filter a series based on specific conditions. In this example, we create a new series representing sales data, where each element corresponds to a sales figure linked with an index label, just like in our previous examples. The significant aspect here is the filtering operation. We want to retain only those sales figures that exceed a threshold, in this case 250. To achieve this, we apply a condition directly to our series, which generates a Boolean mask indicating which elements meet the condition. The code then stores this filtered data in a new series named highSales. This practice allows us to separate the relevant data from the rest, aiding in further analysis without clutter. When we print this new series, it displays only the sales figures that satisfy our condition, showcasing the power of conditional selection. Such filtering empowers data professionals to focus on significant data points, ultimately leading to more insightful analyses and facilitating effective decision-making based on the extracted data. This method exemplifies how selection can be a vital tool in data processing workflows. As we reach the end of this journey into pandas.Series selection, let's take a moment to review our newfound skills. We've explored accessing data by labels and positions, slicing, filtering, checking for the presence of labels, and even combining selections with conditions in exciting ways. Each of these techniques enhances your data manipulation toolkit, allowing you to uncover insights and write cleaner, more efficient code. So whether you're a data scientist honing your skills or just a curious learner seeking to enhance your codesmithing prowess, practicing these selection techniques will skyrocket your comfort with pandas and data analysis as a whole. Keep pushing the boundaries of your understanding, and before you know it, you'll be deftly handling complex datasets with the grace of a seasoned pro. Happy coding. Now let's take a look at how we can create a simple data frame to hold our student information. First, we begin by importing the pandas library, which provides the tools needed to work with data in Python. Next, we define a dictionary called data, where we store our students' attributes, including their names, ages, and grades. Each key in the dictionary corresponds to a column in our data frame: name, age, and grade, while the associated values are lists that contain the actual data for each student. Now we can implement the PD DataFrame data function, which takes our dictionary and creates a data frame named students.df. This data frame organizes our data in a tabular format, allowing us to utilize the powerful data manipulation features of pandas. Finally, by calling print students.df, we will display the data frame, showcasing a neatly structured table with our student data, emphasizing how easy it is to visualize and access information through pandas. Such a structured representation is crucial for effective data analysis, setting the foundation for further selection and filtering operations we'll explore next. Now let's take a look at how to select a single column from our data frame, specifically the name column. By referencing the column label within square brackets, as we do with students.df name, we can effectively isolate this particular dataset. This selection technique is intuitive, allowing you to retrieve just the names of the students while ignoring their ages and grades. When we execute this line of code, it produces a series object containing only the names. This series is a one-dimensional array, making it perfect for our needs when we are specifically interested in one aspect of the data. The output will showcase each student's name alongside their corresponding index in the data frame. This demonstrates the power of pandas for data manipulation and selection, as it simplifies the process of focusing on specific attributes. By extracting individual columns like this, you can easily work with only the data you need for analysis, enhancing both clarity and efficiency in your data operations. Next, we will write the following code to select multiple columns from our data frame, specifically the students' names and their grades. By using double square brackets, we can enclose the column names in a list. This tells pandas that we want to retrieve both name and grade columns simultaneously. When we assign this selection to the variable nameGrade and print it, pandas returns a new data frame that includes just the specified columns, effectively allowing us to focus on the data we are interested in without the distraction of other information like age. This method of selecting multiple columns showcases the flexibility of pandas when it comes to data retrieval. It enables us to extract and analyze specific aspects of our dataset, making it incredibly useful for various analyses in real-world scenarios. As you can see, the output presents a neat table format showing the names alongside their respective grades, enabling easy comparison and further exploration without additional modifications. This capability is vital for efficient data manipulation and helps to streamline the analysis process as you work with larger datasets. Now let's implement the following code to filter our data frame for students who received a grade. We create a new variable called high achievers, which utilizes our data frame students.df. The key part of this code is the condition students.df grade equals A, which generates a Boolean mask, essentially a series of true and false values corresponding to whether each student's grade matches A. This Boolean mask is then used to index our data frame, effectively allowing pandas to return only the rows where this condition is true. As a result, the high achievers variable will contain a subset of the original data frame, showcasing only those students who excelled within a grade. This process highlights the powerful data filtering capabilities of pandas, enabling you to refine your analysis based on specific criteria. Finally, we use the print function to display this filtered data frame, allowing us to easily view and analyze the achievements of the students who reached this academic milestone. This approach not only emphasizes the importance of condition-based filtering, but also demonstrates how to manage and extract meaningful insights from your data efficiently. Now let's see how we can select the first two rows from our data frame using the powerful iloc method. To do this, we'll use the line first two students equals students df iloc02. Here iloc allows us to specify the exact integer index positions of the rows we want to retrieve. By providing the slice 02, we indicate that we wish to access all columns from the rows indexed at 0 and 1. This means we will be selecting the data related to the first two students, Alice and Bob, and it's important to note that indexing is zero-based and exclusive of the upper limit. Once we've selected these rows, we proceed to print the result with print first two students. The output will display a compact view of the specified rows, showing their names, ages, and grades. This technique provides granularity and control over our data selection, making it easier for us to extract specific information efficiently as we analyze the data frame's contents. Such row selection is foundational in data manipulation, helping streamline our analysis process. Now let's see how we can implement a selection that combines both row and column indexing using the iloc method. In our example, we will retrieve the names and ages of the first two students from the data frame. We achieve this by specifying the rows we want to select with the slice notation 02, which targets the first two rows indexed at 0 and 1, while also indicating the specific columns we are interested in by passing a list containing the indices of those columns, which in this case are 0, 1, corresponding to name and age. When we execute this line of code, the data frame responds by returning a new data frame that contains just the selected rows and columns. This ability to simultaneously select multiple rows and specific columns enhances our data analysis capabilities, making it easier to focus on the information that is most relevant for our investigation. The printed output will neatly display the names and ages of the first two students, demonstrating the power and flexibility of pandas in manipulating data frame structures effectively. Now let's see how we can implement label-based row selection using the lock method. In the first code snippet, we retrieve Charlie's information by using the lock method along with the index position 2, which corresponds to Charlie in our data frame. By doing so, we can access all the details associated with that particular student, including his age and grade. The output provides a neatly structured display of his information. Next, we will take a look at how to select specific columns along with a row by using the same lock method. Here we are interested in retrieving both Charlie's name and his grade. By specifying the index 2 for the row and passing a list containing the column labels name, grade, we can efficiently extract relevant attributes without the need for integer-based indexing. This feature lock enhances clarity in our data selection, allowing us to focus on the specific information we need while navigating through our data frame. Now let's see how we can implement more complex filtering conditions within our data frame. In this example, we focus on identifying students who are both older than 23 and have received a grade of A. We accomplish this by using logical operators to combine conditions effectively. The code demonstrates how to create a new variable, filtered students, which stores the results of our query. To construct this query, we place our conditions within brackets, beginning with the expression that filters for students older than 23, represented by students df age 23. We then combine this with another condition checking if the student's grades are equal to a, denoted by student's df grade equals a. The AND operator serves as a logical, and ensuring both conditions must be true for any selected records. When we run this code, we anticipate that the result will be an empty data frame since no students meet both criteria. However, this exercise illustrates the power of layering conditions to narrow down data selection efficiently, especially useful when working with large datasets where precision is essential for analysis. Next, we will write the following code to reset the index of our filtered data frame. This step becomes necessary after we have filtered our data frame to keep only specific rows, such as those students who received a grade or met other criteria. When we filter a data frame, the resulting index may not be contiguous, which can lead to confusion when trying to reference rows later on. By using the resetIndex method with the parameter drop equals true, we ensure that the original index is discarded and a new continuous index starting from 0 is created. This practice not only keeps our data frame clean but also enhances clarity in our data analysis journey. When we print resetDF, we can observe that the rows now have a new tidy index, making references to any specific data points more straightforward as we continue our analysis. Overall, this step aids in maintaining a well-organized dataset, which ultimately contributes to a seamless data manipulation experience with pandas. Wrapping up our discussion on basic selection from a data frame, it's crucial to realize that Pandas transforms how we interact with our data, providing us with immense flexibility and power. Today, we've covered how to perform simple column selections, filter based on conditions, and use both positional and label-based indexing to retrieve rows and columns efficiently. Not only does Pandas streamline these processes, but it also enhances our capability to conduct thorough data analysis with just a few lines of code. As you continue your journey with Pandas, always remember that the ability to access the right data at the right time can dramatically improve your insights and understanding. Keep practicing these selection techniques, experiment with different conditions, accesses, and combinations, and you'll soon master the art of data manipulation in Pandas, making your analyses faster, more efficient, and more insightful. Happy coding! Now let's implement the code to create our initial data frame. We start by importing the Pandas library, which is essential for handling data in Python. The next step involves defining a dictionary named data, where we organize the information about the students. In this dictionary, we have 3 keys: name, age, and grade, each associated with a list of corresponding values. Here, we specify the names of 4 students along with their ages and grades. After setting up our data, we utilize the PD DataFrame function from Pandas to convert this dictionary into a data frame called students.df. This data frame serves as a structured table where each column represents a distinct attribute of the students. Finally, we invoke the print function to display the data frame, allowing us to visualize the student records in a neatly formatted table. This setup forms the foundational structure for our upcoming exercises in column assignment and modification within Pandas. Now let's see how we can implement the assignment of a new column to our data frame. In this example, we want to track the attendance percentage of our students, which is a critical part of their academic performance. We do this by creating a new column named attendance and assigning it a list of values representing each student's attendance percentage. The expression students.df attendance equals 95, 88, 92, 85 allows us to directly add this new column to our existing data frame. When executed, this code seamlessly integrates the attendance data alongside the other columns, which include the students' names, ages, and grades. By updating the data frame in this way, we enrich our dataset, providing a more comprehensive view of each student's performance. After running this line of code, if we print the data frame, we can visualize how the attendance percentages have been incorporated, enabling us to analyze the data even more effectively. This simple yet powerful operation demonstrates the ease with which you can augment your data frame and highlights the practical applications of column assignment in managing and analyzing student data. Now let's take a look at how we can modify an existing column in our data frame. In this case, we need to update the age of the student named Bob, who recently celebrated his birthday, changing his age from 25 to 26. To achieve this, we will use the lock method, which is powerful for label-based indexing. We first filter the students.df data frame to find the row where the name column matches Bob. After locating Bob's position, we specify that we want to update the age column for that row by assigning the new age of 26. This operation is efficient and straightforward, ensuring that Bob's information is accurately reflected in our dataset. Once we run this code, we can print the updated data frame to see that Bob's age has been successfully modified to 26, demonstrating how simple it is to make changes to existing data within a data frame while using Pandas. Now let's see how we can create a derived column that provides additional insights into our data frame. We want to introduce a new column called age in months, which will represent the students' ages in months rather than just years. To accomplish this, we can simply multiply the existing age column by 12. By doing this multiplication for each entry in the age column, we can generate a new column that effectively transforms our data, enhancing the context without needing to refer to other datasets. In the provided code, we assign the result of this calculation directly to students.df age in months. This means that each student's age is being calculated in months, which not only enriches our data frame but also allows for a more comprehensive analysis of age-related insights if, for example, we were to look at age distributions, eligibility for programs requiring age specifications, or comparative studies. When we print the data frame after this operation, we can observe how this new column integrates seamlessly with the existing data, illustrating the power of Pandas for data manipulation. Now let's see how we can implement a scenario that highlights the importance of ensuring the correct length when assigning values to a data frame column. In this case, we are attempting to add a new column named New Attendance to our existing data frame, Students DF, using a list that only contains 3 attendance percentages instead of the 4 required for our dataset. When we run this code, pandas will raise a value error, indicating that the lengths of the new column and the data frame's existing rows are inconsistent. This enforcement acts as a safeguard for data integrity, as it's crucial that the number of values assigned to a column matches the number of rows in the data frame. By highlighting this example, we emphasize that when working with pandas, it's important to always verify that you are adding or modifying columns with the correct number of elements, helping you maintain a clean and valid data structure throughout your data manipulation tasks. Now let's see how we can assign values based on specific conditions within our data frame. In this step, we'll create a new column named Scholarship that designates whether each student qualifies for a scholarship based on their grade. We want to award a yes for students who have an A and a no for everyone else. To implement this functionality, we utilize a list comprehension, which allows us to concisely create a new list in a single line of code. As we iterate through each grade in the grade column, the expression evaluates the condition checking if the grade equals A. If true, yes is assigned to the corresponding entry in the new scholarship column. If not, it assigns no. This efficient method enables us to create the new column seamlessly without the need for complex loops or additional helper functions. Upon executing this code, our data frame will now reflect which students qualify for the scholarship, enriching our dataset with actionable insights. Next, we will write the following code to categorize students based on their attendance records. Here, we're creating a new column in the data frame called Attendance Category. Using the apply function, we apply a lambda function to each value in the attendance column. This lambda function checks if the attendance value is less than 90. If so, it labels that entry as low, indicating underperformance in attendance. Conversely, if the attendance is 90 or higher, it labels it as high, signaling satisfactory attendance performance. This concise method of transforming data not only streamlines the operation, but also enhances the readability of our data frame. After executing this line, you'll see an updated data frame that clearly indicates each student's attendance performance category, thus providing a quick visual reference to assess attendance trends among the students. By effectively implementing this transformation, we gain valuable insights into student attendance, which can help target those who may need additional support or motivation. Now let's see how we can implement the creation and assignment of a new column for students' favorite subjects. First, we create a pandas.Series called Favorite Subjects, where we list the favorite subjects of each student, ensuring that we assign the same indices as those in our existing data frame, Students DF. This alignment is crucial because it allows pandas to match the subject information with the corresponding students without any additional effort on our part. Once the series is created, we can easily assign it to a new column in the data frame named Favorite Subject. This assignment leverages Pandas' automatic index alignment feature, ensuring that each favorite subject is accurately linked to the right student based on their index. Finally, we print the updated data frame to see the newly added column, which seamlessly integrates the favorite subjects into our existing dataset. This approach not only simplifies data manipulation, but also showcases the powerful capabilities of Pandas to handle data alignment automatically. As we draw our discussion towards a close, it's beneficial to remember the implications of column assignment, especially for large datasets. While assigning new columns or modifying existing ones is a common operation, it can become computationally expensive if done repeatedly on large data frames. As such, it's a good practice to minimize unnecessary assignments and to combine operations wherever possible to optimize performance. For example, instead of creating separate columns for age and days, and then another one for categorizing age groups based on that, it's more efficient to perform an operation within a single column assignment whenever feasible. In conclusion, we have navigated the seas of Pandas data frame column assignments, exploring how to create new columns, modify existing data, and assign values based on various conditions. Through practical examples and code snippets, we've seen how accessible and powerful column assignment can be. Remember that mastering these operations not only streamlines your data manipulation efforts, but also enhances your ability to analyze datasets effectively. So keep practicing, pushing the boundaries of what you can achieve using Pandas, and watch your skills grow in this fascinating world of data. Happy analyzing! Integral types are the most basic type category in Pandas. Much like the int type in Python or the integer data type in a database, these can only represent whole numbers. Despite this limitation, these types are essential for various applications, including arithmetic operations, indexing, counting, and enumeration. Working efficiently with integral types is key to high performance, especially when scaling applications or reports. Now let's see how we can work with integral types in pandas by creating a series with 64-bit integers. In this example, we begin by importing the pandas library, which is essential for data manipulation tasks in Python. Next, we create a pandas series that utilizes the built-in range function to generate a sequence of integers from 0 to 2 by specifying dtype equals pd. In 64dtype, we ensure that the series will use a 64-bit integer data type, which offers a high performance for our computations, especially beneficial for larger datasets. After initializing the series, we use the print function to display its contents. The output showcases not only the integer values, but also indicates that the data type is int64, reaffirming that we are working with a 64-bit representation. This is particularly important because the performance during computations will usually be superior compared to using standard Python integers, making this approach an effective way to handle larger integers efficiently in data analysis. Next, we will write the following code to create a pandas series that utilizes floating point numbers. This example illustrates how to represent real numbers with fractions, which is essential in fields like scientific computation and financial analysis. In the code, we initialize a series with values 3.14, 2.718, and -0.577, explicitly setting the data type to PD, float 64D type. This ensures that we are using 64-bit floating point representation, which provides greater precision and a wider range of values compared to 32-bit floats. When the series is printed, it displays the elements along with their corresponding indices and data type. Notably, using PD float 64D type allows for accurate representation of decimal values, essential for any calculations that require precision. However, it's crucial to remember that floating point arithmetic can introduce rounding errors, so understanding how to implement and manage these data types is vital, especially when dealing with very large or small values. This serves as a reminder that while floating point types offer flexibility, their application must be approached with caution regarding performance and accuracy. Now let's take a look at how to create a Boolean series in pandas. Boolean types are pivotal for making decisions in data analysis, allowing you to represent conditions or states simply as true or false. In the provided code, we initialize a Boolean series using the PD_Series function, passing a list that consists of 3 Boolean values, true, false, and true, by specifying the data type as PD. Boolean dtype, we ensure that the series maintains its integrity and explicitly supports Boolean operations without mixing types, which is essential for data consistency. The code then prints the resulting Boolean series, displaying the values alongside their respective index. This structured output allows you to easily identify which values correspond to which condition. Thanks to this clear representation, you can leverage the series in decision-making processes or filter your datasets effectively, helping to simplify analysis tasks and enhancing code readability. Overall, manipulating and checking conditions through Boolean series is a powerful tool in the pandas library. Now let's implement the following code to create a pandas series specifically designed for handling strings. By using the PD string dtype, we can ensure that our data is stored in a way that enhances both memory efficiency and data integrity when manipulating text. In the code, we are initializing a series with 3 fruit names, apple, banana, and cherry, by specifying the dtype as PD. String dtype, we are explicitly indicating that these entries should be treated as string data rather than the generic object type. This distinction is crucial because it helps maintain clean and type-safe code, reducing the potential for bugs related to unintended type coercion. After creating the series, the next line prints the series to the console. The output not only displays the contents but also includes the data type, confirming that we are working with strings as intended. This approach reinforces best practices in data handling, ensuring clarity and efficiency in your data analysis tasks, especially when working with text data in larger datasets. Now let's see how we can implement a pandas series that accommodates a missing value using the PD no identifier. In this example, we create a mixed data series which includes integers by specifying the data type as PD int64D type. This choice allows us to work with 64-bit integers while also being flexible enough to handle the presence of a missing value. By introducing PD.NA into our series, we can observe how pandas seamlessly manages type compatibility. The initial integer value of 1 remains intact, while the second entry demonstrates the handling of a missing value, represented as NA. The final entry is another integer, 3. It's important to note that having a missing value in this series causes pandas to treat the entire series as capable of holding nullable integers, ensuring that we don't lose important information. Understanding this flexibility in data types not only maintains data integrity, but is also crucial when performing operations like filtering or aggregating data. Thus, managing missing values effectively is a fundamental skill when working with large datasets. Now let's take a look at how to create a categorical series in pandas, which is particularly useful for managing data that falls into distinct categories. In the code, we initialize a series with a list of color strings, specifically red, blue, green, and a repeated red. By specifying the data type as category, pandas optimizes memory usage and performance, especially when many values in your data are repeated. This approach not only compresses the data, but also enhances the efficiency of operations like filtering and grouping. When we print the categorical series, each color is designated as a category instead of being treated as a string, presenting us with a clear and concise representation of data. Using categorical types leads to quicker analyses and lower memory overhead, making them invaluable when working with large datasets. This example highlights the importance of understanding and utilizing categorical data types to leverage pandas' capabilities fully in data manipulation tasks, allowing for more efficient data processing in our broader analysis of data frames. Now let's take a look at how to create a DataTime series in pandas. In the code, we initialize a pandas series named DataSeries, which comprises 3 strings representing specific dates, January 1st, 2nd, and 3rd of 2024. Notably, we specify the data type as DataTime 64NS, which is crucial for ensuring that pandas understands these values as dates rather than plain strings. This distinction allows for powerful date manipulations and operations later on. When we print the date series, pandas displays the dates in a user-friendly format while also indicating the data type for clarity. This capability of converting strings to a DataTime type not only facilitates better data organization but also enables a host of time-related functionalities, such as extracting the year, month, or day and performing date arithmetic. Therefore, utilizing the DataTime 64 type streamlines time series analyses, making this a critical tool for anyone dealing with date and time data in their applications. Next, we will write the following code to create a time delta series in pandas, which will allow us to represent and manipulate durations effectively. The code initializes a pandas series containing PD time delta objects, each representing a duration of days. Here we use a list comprehension to create time delta instances for 0, 1, and 2 days, clearly showcasing how to construct intervals of time that can be utilized in various calculations or analyses. When we print the resulting series, we observe a straightforward output indicating each duration in days. This representation is particularly valuable when calculating time differences between 2 dates or conducting time-based analyses, such as event durations or delays between transactions. Utilizing the PD time delta type not only simplifies duration management, but also integrates seamlessly with other date and time operations in pandas, enhancing our ability to perform comprehensive time series analyses. By leveraging the capabilities of time delta, we venture into a vital aspect of temporal data handling, providing us with tools to make our analyses more dynamic and meaningful. Now let's implement the following example using pi-arrow types in pandas. Here, we are creating a pandas series that leverages Apache Arrow's date32 data type. By utilizing PD-arrow dtype par date32, we optimize memory usage and enhance performance when handling date information. The series is initialized with string representations of dates, 2020 40101 and 2020 40102, both of which are then converted into date32 format. This conversion makes it easier to perform various date-related operations while conserving memory compared to using standard object types. Once the series is printed, you'll notice that pandas outputs the values along with their specific D-type, confirming their successful conversion into Arrow's efficient format. This integration illustrates how pandas can work seamlessly with Apache Arrow, providing a standardized and effective approach for managing date types across different analytics frameworks. By adopting this method, you can expect improved interconnectivity and performance, especially when working with large datasets or different data systems. In conclusion, understanding the diverse data types offered by pandas is critical for effective data manipulation. We've covered integral, floating point, Boolean, string, categorical, and temporal types, along with their nuances in handling missing values and performance considerations. Mastering these types isn't just about knowing how to use them, it's about using them to optimize performance, manage memory effectively, and maintain data integrity. So far, we learned about pandas' data frames, focusing on column assignment and the significance of this operation in data manipulation. We explored how to create a data frame, select and modify columns, and assign new values based on conditions. Additionally, we discussed the importance of matching lengths and the implications of modifying large datasets efficiently. Now, we will continue to enhance our understanding of how to work with data frames effectively. Let's dive into the exciting world of temporal types in pandas. In this lesson, we will focus on how to manage date and time effectively in our data analysis tasks. So far, we learned about the various data types in pandas, including integral, floating point, Boolean, string, categorical, and temporal types. We explored their significance in data manipulation, efficiency in memory usage, and handling of missing values. Understanding these types is crucial for optimizing performance and maintaining data integrity. Next, we will enhance our knowledge of temporal types and how they can be expertly managed in our data frames. Unlike many database systems that offer separate date and DAT, TIME, or timestamp data types, Pandas provides a single data time type. This unique design means you can use the same type for both date and time, which makes our lives a whole lot easier. You can construct this data time type using the dtype argument with the datatime 64-unit form, where the unit can be nanoseconds, microseconds, milliseconds, seconds, minutes, hours, and days. This flexibility helps us handle different granularity levels in timestamps without feeling constrained by the standard formats. Now, let's take a moment to see how we can create a data frame with different data time types. Now let's see how we can create a data frame containing data time values in Pandas. We start by importing the Pandas library, which is essential for handling data in Python. The code then creates a date range using the pd_dateRange function, specifying a start date of January 1, 2024, and generating a total of 5 consecutive days with a daily frequency. Next, we proceed to construct a data frame named dfDates. In this data frame, we define 2 columns, one for our generated dates and another for fictional temperature data represented as a list with values for each corresponding day. This demonstrates how we can tie together data time values and numeric data within a single data frame. Finally, by using the print function, we display the data frame, allowing us to visualize the dates alongside their respective temperatures. This approach not only highlights the efficient management of date and time in Pandas, but also sets a solid foundation for further temporal data analysis tasks, such as extracting specific components, calculating differences, and managing time zones. Now let's explore how we can extract specific components from our datatime object in the data frame. We begin by adding 4 new columns that will enhance our analysis by providing detailed information about the dates in our dataset. First, we utilize the DT accessor to extract the year from the date column and create a new column called year. This makes it easy to analyze trends over different years. Next, we repeat this process for the month and day, adding corresponding columns named month and day. Each of these new columns allows us to break down our dates into more manageable components that lend themselves to various types of analysis. Finally, we also capture the day of the week by using the dayname function, storing this information in a column called day of week. When we print the updated data frame, we can observe the original date alongside the newly created columns that summarize its attributes, making our data much clearer and insightful for further analysis. This structured breakdown of the data time values conclusively enhances our ability to derive meaningful insights from the data. Next, we will write the following code to analyze temperature changes in our data frame. First, we use the diff method on the temperature column to calculate the difference in temperature from one day to the next, thereby creating a new column titled temp change. This column will provide insights into how much the temperature fluctuated daily, allowing us to observe trends over time. In addition to tracking temperature changes, we will also create a column called days since start. To do this, we subtract the minimum date in our date column from each date entry, effectively calculating the number of days that have elapsed since the first recorded temperature. This new column, expressed in days, will help us measure the time duration of our observations in a clear and straightforward manner. Finally, by printing the data frame, we will get a comprehensive view that includes both the calculated temperature changes and the duration in days since the start. This will not only enhance our dataset, but also provide valuable insights into temperature trends, essential for any data analysis related to time series. Now let's see how we can implement time zone functionality in our data frame. First, we localize our dates to Coordinated Universal Time (UTC) using the TZ-localize method. This step is crucial when we deal with datatime data originating from different time zones, as it defines a reference time zone for our datatime values. By localizing to UTC, we ensure that our timestamps are standardized, facilitating subsequent conversions. Next, we convert these localized dates to Eastern Time, New York, using the TZ-convert method. This allows us to see the same moment in time reflected in New York's local time zone, which is particularly important for datasets containing time-sensitive information across various regions. The resulting data frame now features both the original dates and the converted datatime values, enabling us to easily compare and analyze time-based data from different locales. This approach is invaluable in data analysis, ensuring accuracy and consistency when interpreting temporal phenomena. Now let's see how we can handle missing datatime values in our data frame. We simulate a scenario where a timestamp is missing by introducing a NUT value. This is done using the lock method to specifically target a row and set its date column to PD NUT, which represents a missing datatime entry in pandas. Next, we implement the fillNum method to address the gap left by the missing value. We use the forward fill option method equals ffill, which propagates the last valid observation forward to fill in the missing timestamp. This technique ensures that the data frame remains continuous and helps maintain data integrity for subsequent analyses. Finally, by printing the updated data frame, we can observe how the missing value has been seamlessly filled, resulting in a consistently structured dataset. This functionality is crucial when processing real-world data, as it allows for a smooth analysis, ensuring that missing timestamps do not disrupt the flow of data handling or interpretation. Now let's see how we can summarize our daily temperature readings into weekly averages, which is an essential technique in time series analysis. The code we will write uses the resample function, a powerful tool in pandas that allows us to change the frequency of our time series data. In this case, we specify W as the frequency, indicating that we want to group our daily data into weekly intervals. By applying the mean function on the resampled data frame, pandas automatically calculates the average temperature for each week based on the corresponding daily readings. The resulting data frame, weekly AVG, will present a cleaner, aggregated view of temperature trends over a longer period, helping us to more easily identify patterns and fluctuations throughout the weeks. This aggregation is invaluable when analyzing data that spans extended time frames, as it reduces noise and highlights underlying trends, ultimately making your analyses more insightful and manageable. Additionally, such transformations can pave the way for further analysis, such as seasonal trends or comparisons across different time periods. Now let's implement the following code to visualize our daily temperature data over time using matplotlib. We start by creating a new figure with a specified size of 10 by 5 inches to ensure our plot is clear and easily readable. The pltplot function is then called to generate a line graph, where we plot the dates on the x-axis and the corresponding temperature values on the y-axis. We also include a marker for each data point, labeled daily temperature, which helps in identifying the individual temperature readings more distinctly. To enhance the plot's informative nature, we add a title that summarizes the content of the graph, along with descriptive labels for both the x-axis and y-axis. It's important to format the x-axis ticks for better readability, especially since dates can be closely packed. Hence, we rotate the tick labels by 45 degrees. Additionally, we enable a legend to denote what the data points represent. Finally, by employing PLT-tight layout, we ensure that elements of the plot do not overlap, leading to a polished look before we call PLT show to display the completed plot. This visual representation is integral for identifying temperature trends that might not be apparent in tabular formats. As we explore the depth of temporal types in pandas, it's crucial to remember the myriad of features that enhance data integrity and facilitate complex analyses. We've discussed extracting datatime components, handling time deltas, managing time zones, addressing missing values, resampling, and visualizing data. Each of these capabilities enhances our efficiency, enabling us to tackle sophisticated data challenges in the real world. In conclusion, mastering the handling of temporal types in pandas significantly enhances your data analysis toolkit. With the ability to manipulate dates, times, and their associated data intelligently, you empower yourself to derive richer insights and make data-driven decisions more effectively. Whether you're tracking sales figures, analyzing climate data, or working on project timelines, these skills are invaluable. Continue practicing these concepts, and you will find yourself navigating the world of time-based data like a pro. Understanding categorical data types in pandas is crucial for optimizing data analysis. The main point of the categorical data type is to define an acceptable set of domain values that your PD series can contain. With categorical data, you can better represent data that has a fixed number of possible values, such as gender, education levels, or the names of countries. This can significantly reduce memory usage and improve performance during data analysis. So far, we have learned about managing date and time effectively in pandas, and now we will cover how to efficiently use categorical data types to enhance our data manipulation capabilities. Now let's take a look at how to create a simple data frame to illustrate the use of categorical data types in pandas. First, we import the pandas library as PD, a common practice that allows us to access its functionalities easily. We then define a dictionary called data, which consists of two keys, car brand and sales. The car brand key holds a list of different car brands, while the sales key contains the corresponding sales figures. With this dictionary, we proceed to create a data frame named DF using PD DataFrame data. This data frame effectively organizes our data into a tabular format, making it easy to manipulate and analyze. By calling print.df, we can display the data frame, showcasing the initial setup and the data it holds, which sets the stage for further operations with categorical types. The limited number of brands in the car brand column hints at the efficiency gains we can achieve by converting this column to a categorical data type. Next, we will write the following line of code to convert the car brand column to a categorical type. This transformation reduces memory usage and speeds up data operations by representing these categories under the hood as integers rather than strings. Now let's see how we can inspect the categorical nature of our data after converting the car brand column to a categorical type. We can access vital information about our categories and their integer codes using the cat accessor. The first line of code retrieves the unique categories in the car brand column, which allows us to see all car brands represented in our dataset, such as Toyota, Honda, Ford, and Chevrolet. This is particularly useful for confirming that the transformation into categorical type has been successful and to understand what categories we are working with. Next, we will write the following line to obtain the integer codes associated with each category. This line provides a practical way to visualize how pandas internally represents these categorical values as integers for optimized processing. Essentially, this transformation enhances our analytical capabilities, enabling faster aggregations and operations on the car brand data compared to when it is treated as plain strings. Understanding these aspects sets a strong foundation for subsequent analysis, like calculating total sales per car brand, which we will explore next. Now let's implement the following approach to sort categorical data according to a specific order. We begin by defining the desired order of car brands using categorical dtype, where we explicitly set the categories as Toyota, Honda, Ford, and Chevrolet, specifying that this order matters. This step is crucial because it ensures that when we later sort our data frame, the car brands will appear in the exact sequence we've defined, rather than in an arbitrary alphabetical order. Next, we cast the car brand column in our data frame to use this new ordered categorical type. This ensures that the data frame recognizes the established order when performing any sorting operations. After transforming the data type, we can then sort the data frame based on the car brand column using the sort values method. This operation effectively rearranges the data frame to reflect the order we set up earlier. Finally, we print the sorted data frame, which will nicely display our car brands in the desired order, making it easier to analyze and interpret the data according to our established hierarchical structure. Now let's see how we can handle missing values in our categorical data by introducing a special category for any unknown entries. We'll start by using the add categories method from the pandas library, which allows us to add a new category called unknown to our existing car brand column. This is particularly useful when we have data that might not fit into one of our predefined categories, ensuring that we don't lose any valuable information due to missing data. Next, we will assign an unknown value to a specific row in the data frame, in this case, the one at index 3. By doing this, we effectively categorize this entry as unknown, allowing us to maintain the integrity of our data while acknowledging that some information is missing. This approach provides us with a robust dataset where all entries have clear, defined categories, making our analysis more resilient and comprehensive, even when faced with imperfect data. Finally, we will print the updated data frame to see the changes reflected in our car brand column, now complete with our new category. Now let's see how we can implement a transformation to combine two related categories in our data frame. In this example, we want to merge the car brand Toyota with Lexus to create a single category labeled Toyota and Lexus. This code leverages the category method rename categories, which allows for straightforward modification of category names directly within the original data frame. By executing this line, we are not only simplifying our dataset, but also enhancing its clarity and relevance, particularly when preparing for data visualization or machine learning tasks. The transformation seamlessly adjusts the categorical data without the need to create a new column or data frame, illustrating the efficiency and flexibility offered by Pandas' categorical data types. After the execution of this command, we can use the print function to output the updated data frame, clearly showcasing the changes in the car brand column. This approach ensures that our data remains organized and informative, reflecting any necessary changes in our analysis effectively. Now let's see how we can convert our categorical data into a format suitable for machine learning. Using the Pandas library, we can leverage the getDummies function to perform one-hot encoding on our car brand column. This technique generates a new data frame where each category within car brand is transformed into its own binary column. Importantly, we specify the drop first parameter as true to avoid the issue of multicollinearity, where one column can be perfectly predicted from the others, which could skew our model's performance. By dropping the first column, we ensure that our model captures the necessary information without redundancy. The resulting data frame will allow machine learning algorithms to correctly interpret these categorical variables, effectively treating them as distinct features rather than as a single string variable. Furthermore, this approach not only enhances model training, but also contributes to improved accuracy in predictions, showcasing the efficiency of transitioning to numerical representations for categorical data. After running this command, we can print the encoded data to examine how the transformation has unfolded and confirm its suitability for our modeling endeavors. Now let's see how we can implement data visualization to gain insights from our car sales data. We will create a bar chart that showcases the total sales for each car brand, which visually summarizes the information we've analyzed so far. First, we use Pandas' Group B method to aggregate the sales data by the car brand. This operation sums the sales for each brand, providing a clear overview of performance across different categories. Next, we utilize the plot method from Matplotlib to create a bar chart, specifying kind equals bar to indicate the desired visualization type. The color parameter is set to sky blue to enhance the visual appeal of the plot, making it more engaging to the viewer. To improve clarity, we also add a title to our chart, along with labels for the x-axis and y-axis. These labels help viewers quickly grasp the meaning of the data being presented. Finally, the xsticks method is used to rotate the x-axis labels for better readability, especially since car brands might have longer names. When we call PLT show, the chart is displayed, giving us a powerful visual representation of our sales data. Now let's see how we can implement the removal of unnecessary categories from our categorical data. In our example, if we determine that the Chevrolet category is no longer relevant to our analysis, we can streamline our data frame by removing it. This step is crucial for maintaining an efficient and tidy dataset, especially as projects evolve over time. To achieve this, we can utilize the Remove Categories method available for categorical data in Pandas. By applying this method to the car brand column, we specify the category we want to eliminate, in this case, Chevrolet. After executing this line of code, the data frame will no longer include this category, thereby enhancing performance and clarity in our analysis. Such a cleanup process helps us focus on the categories that truly matter for our insights, making the analysis more straightforward without the distraction of unused or irrelevant data points. Finally, we can print the updated data frame to confirm that the Chevrolet category has been successfully removed, showcasing the effectiveness of our data management practices. In conclusion, effectively using categorical data types in Pandas enhances both performance and clarity in data analysis. By converting regular string fields to categorical types, you reduce memory usage, accelerate operations, and improve the overall efficiency of your data analysis tasks. We covered creating, sorting, and handling categorical data, optimizing it for machine learning, visualizing results, and maintaining clean project data. Mastering these concepts will empower you to conduct sharper insights and make informed decisions based on the analyses you perform. Remember, whether you're dealing with sales data, survey results, or demographic information, utilizing categorical data types will always be a game changer in your data science journey. In the world of data analysis today, understanding data types is crucial. They govern how data is handled, manipulated, and transformed within data structures, shaping the way we interact with our data. Today, we are going to delve deep into the various types of data, particularly focusing on how to interact with JSON using the pandas library in Python. So far, we've learned about categorical data types in pandas, exploring their significance in optimizing memory and enhancing performance. Now we will cover the use of JSON in data analysis, specifically how to read and write JSON data using pandas and the different formats in which we can structure this data. We will explore the various ways to represent tabular data in JSON and how to efficiently convert it back into a pandas data frame. By the end of this tutorial, you will be equipped with the knowledge to handle JSON data seamlessly in your analytics workflows. Now let's see how we can implement the process of loading JSON data into a pandas data frame. First, we begin by importing the necessary libraries, pandas, which is essential for data manipulation, and JSON, which allows us to work with JSON formatted data in Python. We presuppose that our JSON data is stored in a string format, representing band members of the Beatles. Next, we use the JSON loads method to convert this JSON string into a Python dictionary. This step is crucial as it transforms the raw JSON format into a structure that Python can easily interact with. Following that, we utilize PD.JSON normalize to flatten the data into a structured data frame. This method efficiently breaks down the nested JSON, allowing us to access each member's details, first name, last name, and birth year in a tabular format. Finally, we print the data frame to visualize the structured output, which reveals the members and their respective information. This approach exemplifies how effortlessly we can convert JSON data into a format that is conducive for analysis in pandas. Now let's see how we can implement writing a data frame back to JSON format using the pandas library. We'll begin by creating a data frame named Beatles.df, which contains information about two members of the Beatles, Paul McCartney and John Lennon. This data frame consists of 3 columns, first, last, and birth, representing each member's first name, last name, and birth year, respectively. Once we have our data frame set up, we'll focus on converting it into a JSON format using the toJSON method from pandas. By setting the orient parameter to records, we instruct the method to structure each row of the data frame as an individual JSON object within an array. This orientation effectively creates a simplified representation of our data, making it easy to transmit, especially to web applications or APIs. After invoking the method, we can print the output. You'll notice that the resulting JSON string contains nicely formatted objects for each member, making it ideal for integration with REST services. This flexibility showcases how pandas helps bridge the gap between data frames and JSON, enabling seamless data exchange in various applications. Now let's take a look at how we can write a data frame back to JSON using the split orientation. This orientation is particularly useful when we want to maintain a clear distinction between the index, column labels, and the data itself. We start by calling the toJSON method on our data frame, Beatles.df, and specify orient equals split. This results in a JSON object structured to include 3 key components: an array of indices, an array of column names, and the actual data represented in a nested array format. Once we execute this command, we can print the resulting JSON object to visualize the output. What you'll observe is a neatly organized representation that allows for easy interpretation of the data frame structure. The index is presented as an array, followed by the column names, and the data is encapsulated in its own array. By employing the split orientation, we achieve a JSON format that effectively communicates both the layout of the data and its contents, which can be particularly beneficial when dealing with complex datasets or when metadata about the data structure is essential for subsequent analyses. Now let's see how we can read JSON data with a specific orientation using pandas. In the following code, we utilize the PD read JSON function which allows us to bring our JSON data into a DataFrame format seamlessly. The IOString function is employed here to convert the JSON string JSON split into a file-like object which is necessary for PD read JSON to interpret it correctly. By specifying the orient parameter as split, we align our reading method with how the JSON data was structured during export. When we print the resulting data frame, it reflects our original data in a tabular format, accessible for further analysis and manipulation. This method is particularly advantageous when working with various structures of JSON data, enabling flexibility in how we can manage our datasets within Pandas. Understanding this approach can significantly enhance your ability to manipulate and analyze JSON data effectively. Now let's see how we can implement the normalization of nested JSON data using Pandas. In this example, we have a JSON structure containing a list of records, each representing an entity with characteristics, along with pagination metadata. To focus on the relevant records, we first define a dictionary that mimics the original JSON structure. Next, we utilize the PD.JSON normalize function specifying the record path parameter to directly access the records within the nested data. This function flattens the JSON structure, transforming the nested characteristics into separate columns in the resulting data frame. As a result, we achieve a clear tabular format where each row corresponds to an entity and its associated attributes, such as the number of legs and eyes. This method not only simplifies the data analysis process, but also helps in efficiently handling complex JSON structures common in APIs. By employing PD.JSON normalize, we can effectively extract the necessary information while disregarding any extraneous metadata, making our analytical tasks more straightforward and targeted. Furthermore, managing missing values in JSON can also be a challenge. JSON structure doesn't inherently deal with missing values, meaning we often must handle them after reading the data into Pandas. After normalizing, we can easily check for missing values using df-isna and impute or fill them as needed using df-fillna method as necessary. In conclusion, we've covered a broad range of topics today, from the basics of JSON structure to the intricacies of reading and writing JSON with Pandas. By mastering these techniques, you can manipulate and analyze data efficiently, directly inserting JSON into your analytical workflows while efficiently handling its various formats. Whether it's reading from APIs, saving results, or transforming datasets, understanding how to work with JSON in Pandas will significantly enhance your data analysis toolkit. So roll up your sleeves, start experimenting with JSON in your data analysis projects, and remember, the better you understand your data types, the more effectively you can wield the power of data analytics. Now let's explore how we can efficiently read specific columns from a CSV file using Pandas to optimize memory usage. First, we start by importing the Pandas library, which is essential for data manipulation in Python. Next, we specify the path to the CSV file containing our customer data. By calling the readCSV function, we can utilize the usercalls parameter to specify the exact columns we want to read, in this case, customer ID and purchase amount. This selective loading prevents unnecessary memory allocation for other columns that we do not require, ensuring that we only reserve memory for the data that is critical to our analysis. Finally, after loading the relevant data, we display the first few rows of the data frame using print_df head. This output allows us to verify that we have successfully extracted just the columns we need. By implementing this method, we significantly reduce our overall memory consumption, which is especially beneficial when working with large datasets. Now let's implement the following strategy to optimize memory usage by explicitly defining data types for our data frame columns. We start by creating a dictionary named dtypes, which specifies the data types we intend to use for each column in our dataset. For instance, the custom ID column is assigned the int32 type, assuming that customer IDs will fit within this range. The age column is set to int8, which is sufficient for storing age values, while the purchase amount is defined as float32 to save memory without compromising the precision needed for purchase amounts. Next, we will use the PD_readCSV function to load our data from the CSV file. In this step, we pass both the usercalls parameter to select only the relevant columns, customer ID, age, and purchase amount, and the dtype parameter to apply our previously defined data types. This careful specification not only limits the memory used by the data frame, but also streamlines the data loading process. Finally, we utilize print_df info to display the DataFrame summary, which confirms that the data types have been set correctly, allowing us to visualize the memory efficiency achieved through this technique. Next, we will implement a strategy to handle missing values in our data frame, specifically focusing on optimizing memory usage. In the provided code, we start by filling any missing values in the age column with -1. This approach prevents the creation of a float 64 column, which would be necessary if we left none values. Instead, by using -1 as a flag for unknown ages, we can cast the age column to a smaller data type, int8, which consumes significantly less memory than the default int64. It's important to recognize that using flag values can enhance data integrity while reducing memory overhead. Additionally, should the age column not be essential to our analysis, we have the option to drop it altogether, freeing up even more memory. This flexibility allows us to make informed decisions about our dataset structure, ensuring that only necessary data is retained. Finally, we finish by calling printdf info to display the DataFrame summary, which includes information about the memory usage and the data types, confirming our optimizations were successful. Now let's see how we can implement chunking to manage memory effectively when processing large datasets. We begin by defining a variable chunk size with a value of 10,000 to specify the number of rows we'll read at a time. This approach allows us to handle large CSV files more efficiently, minimizing memory usage. Next, we create an empty list called chunks, which will store the process segments of the data. By using a for loop, we read the CSV file in smaller chunks with the pd_read_csv function specifying the chunk size parameter. This means instead of loading the entire dataset into memory at once, we process each chunk sequentially. Within the loop, we can perform operations on each chunk, such as filtering it to keep only those records where the purchase amount exceeds 100, signifying significant purchases. Each filtered chunk is then appended to the chunks list. After finishing processing all chunks, we concatenate them into a final data frame using the pd_concat method while ensuring index continuity with the ignore index equals true parameter. Finally, we can inspect the shape of the resulting data frame, which tells us the total number of rows that met our criteria, demonstrating how this method efficiently manages memory without sacrificing performance. Now let's implement the following code to save our processed data frame efficiently. Using the toCSV method, we are writing our data frame final df to a CSV file named processed customer data CSV. However, to enhance memory efficiency and reduce storage costs, we will leverage compression by specifying compression equals gzip. This option tells pandas to compress the data before saving it, which significantly decreases the file size, thus improving storage performance and speeding up time when loading the file later on. By opting for compression, we not only conserve disk space but also optimize the process of data handling. This is especially beneficial when dealing with large datasets that would otherwise occupy considerable memory resources. It's essential to incorporate such practices when saving files, as they lead to both immediate and long-term savings in memory usage. In summary, through the use of compressed CSV files, we are ensuring that our data handling is more efficient and cost-effective, enhancing overall performance in our data analysis efforts. Now let's take a look at how we can create a view of a data frame, which allows us to work more efficiently with memory. We initiate by selecting specific columns, customer ID and purchase amount from the original data frame without making a copy of the entire dataset. This is a key feature of views. They reference the original data, which means they occupy less memory and avoid the overhead of duplicating large amounts of data. Next, we make a modification within this view by applying a 10% increase to the purchase amount, simulating a discount adjustment. It's important to note that changes made to the view will not alter the original data frame, preserving the integrity of the initial dataset. This is particularly useful for exploratory data analysis, where we may want to manipulate data temporally without permanent effects. Finally, we use the head method to display the top entries of the modified view, allowing us to verify the changes made. By utilizing views in this manner, we not only streamline our computations, but also enhance performance when dealing with large datasets. Now let's see how we can implement the groupby method to aggregate our data frame based on customer purchases. In the code, we begin by using the groupby function on the data frame df, specifying the custom ID column as the key to group the data. By doing this, we are organizing the data frame so that all entries corresponding to each unique customer are brought together. This operation is crucial for summarizing data since it allows us to analyze how much each customer has spent. Following the group B, we use the sum function to calculate the total purchase amounts for each customer identified by their custom ID. The as index equals false argument is helpful here, as it ensures that the resulting aggregated data frame summary DF retains a standard integer index instead of using custom ID as the index. Finally, by utilizing print summary DF head, we can display the first few rows of our summarized data frame, giving us a quick overview of the total purchases per customer. This example showcases how effectively leveraging built-in pandas methods can enhance memory efficiency and computational performance in our data analysis tasks. In summary, memory efficiency is a crucial aspect of data analysis that deserves our careful attention. By implementing strategies such as selectively reading columns, explicitly defining data types, handling missing values wisely, chunk processing, using compression, working with views, and leveraging optimized pandas methods, we can significantly improve memory utilization when working with large datasets. These practices will empower you as data analysts and scientists to handle significantly larger datasets and perform analyses that were once thought impractical. As we continue to navigate the world of big data, being conscious of memory efficiency will set you apart in your analytical prowess. Embrace these strategies, and you'll not only boost your productivity but also make your code cleaner and more efficient. Another great feature of the Apache Parquet format is its support for partitioning, allowing us to distribute and organize data more effectively than being confined to a single file. This capability makes Parquet an excellent choice for large-scale data analytics, especially when working with complex datasets. So far, we learned about strategies for improving memory efficiency in data analysis using Python, particularly with JSON data and pandas. We discussed the importance of selecting essential columns when reading CSV files to optimize memory usage, along with specifying data types to reduce memory consumption. Additionally, we explored techniques for handling missing values, chunking large datasets, leveraging compression, creating views instead of copies, and utilizing optimized pandas methods. Now, we will dive into the concept of partitioning in Apache Parquet and see how it can enhance our data organization and accessibility. Partitioning is pivotal when dealing with large datasets, as it divides the data into distinct and manageable subsets based on specific fields or column values. Imagine you have a vast dataset containing user activity logs for different regions. Without partitioning, querying data specific to a region would require scanning the entire dataset. However, with partitioning, we can stack each region's data into its own compartment, allowing for a much more efficient query. This not only speeds up data processing, but also optimizes the performance of analytical queries. With partitioning, systems can read only the necessary segments of data, significantly reducing read times and memory usage. Now let's implement the following code snippet to demonstrate how we can save our data frame in Parquet format while utilizing partitioning. We begin by importing the essential libraries, including pandas for data manipulation and Spark session to handle our Spark operations. Next, we create a Spark session, which is necessary for any Spark application. This session acts as an entry point for interacting with Spark's functionality. Once we have our session set up, we define a sample dataset that includes sales information, such as order IDs, customer IDs, regions, and order dates. This dataset is represented as a dictionary, which we then convert into a pandas data frame for initial manipulation. After preparing the data frame, we convert it to a Spark data frame. This transformation is crucial as it allows us to leverage Spark's distributed capabilities. Finally, we demonstrate the power of partitioning by saving the Spark data frame in Parquet format, where we specify partitioning by the region column. This arrangement results in the creation of different directories for each region, optimizing data access and query performance when we need to analyze sales data based on geographical regions. Now let's see how we can load and query partition Parquet data using PySpark, which allows for efficient data retrieval by leveraging the appropriate partitions. First, we initiate the process by reading the partition Parquet file into a data frame. This line of code efficiently loads the data stored in a structured format, making it readily accessible for querying. By doing this, we allow Spark to recognize the different partitions based on the specified column, in this case, the region. Next, we apply a filter to our data frame to focus solely on the sales data for the North region. This step is crucial as it demonstrates how we can harness the power of partitioning to optimize our queries. Instead of scanning the entire dataset, Spark intelligently uses the partitioning information to only read data relevant to the specified filter criteria. Finally, we display the results of our filtered data frame. This action not only verifies the successful execution of our query, but also showcases the efficiency of partitioned data access, as we are able to retrieve specific information quickly without unnecessary overhead. Overall, this approach illustrates the practical advantages of partitioning in improving query performance. Now let's examine how we can implement partitioning in Apache Parquet to enhance data organization and accessibility. The provided code snippet demonstrates how to write a Spark DataFrame to Parquet format while partitioning the data by the order date column. This process is crucial for optimizing how we store our data since it organizes the dataset into directories based on unique order dates, creating a logical structure that aligns with how the data will likely be queried. As the data frame is written, Spark automatically creates a directory for each unique order date, facilitating quicker data access when performing queries filtered by that date. This approach minimizes the amount of data scanned during analysis, which significantly improves performance, especially for large datasets. By partitioning the data thoughtfully, we not only streamline storage, but also enhance the efficiency of subsequent analysis tasks. Implementing such partitioning strategies can lead to better resource utilization and reduced processing times, making this technique essential for applications involving substantial data analytics. Now let's implement a code snippet that effectively demonstrates how to balance partitions when saving aggregated data. In this example, we first perform an aggregation on our data frame, partition DF, by grouping the data based on the region column. Specifically, we count the number of orders and customers associated with each region using the group by and agg methods. This step is crucial because it helps to reduce variability in the volume of data across partitions, which in turn promotes more balanced and efficient processing. Once we have our aggregated data frame ready, we proceed to save it in Parquet format while partitioning by the region column. This operation is performed using the write partition by function. The result is a new Parquet file titled Aggregated Sales by Region Parquet, which organizes the data into distinct partitions based on the regions. By ensuring that partition sizes are comparable, we optimize the performance of subsequent analyses, allowing queries to execute more efficiently. This approach not only enhances data accessibility, but also aligns with best practices for managing partitioned datasets in large-scale analytics. Now let's implement the following code to group our sales data by region in a distributed manner using Apache Spark. In this example, we use the group by method on our partition data frame, partition DF, where we specify the column region as the key for grouping. This operation aggregates the data, applying the specified aggregation function in this case, counting the number of ordered entries for each region. By leveraging Spark's distributed computing capabilities, each partition of data is processed concurrently across different nodes in the cluster, resulting in significant performance improvements compared to traditional single-node processing. After the grouping and aggregation are performed, we utilize the show method to display the results, allowing us to quickly visualize how many orders were processed in each geographical region. This concurrent processing not only enhances data retrieval times but also optimizes resource utilization within the Spark framework, highlighting how partitioning can be a powerful ally in large-scale data analytics. By strategically grouping and aggregating our data, we set the stage for deeper insights into regional sales performance, ultimately aiding in more effective business decision-making. In summary, partitioning in Apache Parquet is a powerful feature for managing large datasets effectively. The ability to segment data based on specific columns not only enhances data organization but significantly speeds up query performance by minimizing the data scanned during analysis. So far, we've explored the concept of partitioning, how to implement and manage it using PySpark, and critical considerations like optimal partition sizes and query patterns. As you incorporate partitioning into your data processing workflows, you'll realize that it enhances both the efficiency and productivity of your data analysis tasks. Thank you for joining me today on this exploration into partitioning in Apache Parquet. I hope you feel empowered to implement these strategies in your own projects and maximize your data capabilities. The world of data manipulation can be exhilarating, especially when you dive into the practical aspects of Python's pandas library. Today, we're opening the door into basic arithmetic operations using pandas.Series, which is the simplest data structure offered by pandas. By the end of this session, you'll understand how addition, subtraction, multiplication, and division work with pandas.Series, along with useful code snippets to illustrate these concepts. So far, we covered the importance of partitioning large datasets in the Apache Parquet format. Now, we'll focus specifically on arithmetic operations in a PD series. Now let's see how we can create a simple pandas series using a range of numbers. First, we need to import the pandas library, which is essential for working with series and data frames. We then initialize the series by using the PD_Series constructor, passing in a range of numbers generated by the range3 function. This generates a sequence of integers from 0 to 2. Here we also specify the data type as PD. int64d type, ensuring that our series can hold integers with the possibility of having missing values if necessary. After creating our series and storing it in the variable SIR, we use the print function to display its contents. When you run this code, you will observe that the output consists of index labels ranging from 0 to 2 with corresponding values of 0 to 2. This shows that SIR is now a well-structured pandas series, primed for any further data manipulation or arithmetic operations we might want to perform in subsequent lessons. It's a foundational step that opens the door to much more complex data analysis tasks. Now let's see how we can implement addition in our series. By using the plus operator, we can add a scalar value to every element in the series effortlessly. In this case, we assign the result of adding 42 to our series SIR to the variable result_add. This operation utilizes broadcasting, which means that the scalar value 42 is applied to each entry within the series without requiring explicit iteration through the elements. After executing the operation, we can display the results by printing result_add. The output should reflect that 42 has been added to each element. The first element becomes 42, the second element becomes 43, and the third element becomes 44. This demonstration highlights the power and simplicity of performing mathematical operations with pandas series, illustrating how intuitive and efficient data manipulation can be with the pandas library. By leveraging Python's inherent capabilities in combination with pandas, working with data becomes seamless and straightforward. Next, we'll explore how to perform subtraction using the operator. Now let's implement the following code, where we subtract the scalar value of 42 from each element in our previously defined pandas series, SIR. The operation result_SIR42 effectively decrements each value in the series by 42, showcasing the power of broadcasting in pandas. The new series resulting from this operation is then printed out using print result_sub. When you run this code, you'll notice that every element in the series has been reduced by 42. Specifically, if the original series contained the values 0, 1, and 2, the resulting series will show -42 and correspondingly. This demonstrates how subtraction, much like addition, operates seamlessly across all elements without requiring any loop. Such functionality makes data manipulation in pandas intuitive and efficient, allowing you to perform calculations on datasets easily and effectively. Just like addition, the broadcasting feature ensures that the operation is applied to each entry, highlighting the flexibility of pandas in handling arithmetic computations. Next, let's take a look at multiplication. To multiply each element in the series by a scalar, we simply use the asterisk operator. This operation will apply the scalar multiplication across all elements of the series without the need for loops, thanks to pandas' efficient broadcasting capabilities. Now let's implement the following line of code. Result mul equals SIR*2. This line creates a new variable, result mul, which stores the result of multiplying each value in the original series, SIR, by 2. When we print result mul, we can see that each element has been accurately multiplied by 2, yielding the values 0, 2, and 4. The output format retains the index labels from the original series, making it easy to reference each result in relation to its corresponding index. This demonstrates how straightforward arithmetic operations can be performed on a pandas series, allowing us to effortlessly scale our data for further analysis. With this understanding, you're now equipped to manipulate series elements using multiplication and prepare them for advanced data operations. Now let's take a look at how we can perform division on our pandas series. With the division operator /, we will divide each element in the series SIR by 2. This straightforward operation demonstrates how pandas allows us to effortlessly manipulate data using arithmetic operators, just like in standard Python. When we execute the code to divide SIR by 2, pandas applies the division to each individual element, resulting in a new series named resultDiv. The output of this operation will showcase that each value has been halved, yielding a floating point result. It's important to note that despite the input series being of an integer type, rounding down is not a factor here. Thus, pandas returns floating point numbers for the division operation. With output indicating values like 0, 0.5, and 1, this result reflects pandas' ability to handle different data types efficiently, automatically promoting integer values to floats when performing division. Understanding this behavior is crucial for data analysis, as it ensures that calculations maintain precision, especially when dealing with non-integer numbers. Now let's take a look at how to create a second pandas series, which will allow us to explore arithmetic operations between two series. We initiate this by defining SIR2, which is created using the PD_Series function, and we populate it with a range of integers from 10 to 12. The data type is specified as PD_int64D type, ensuring we retain the integer format even when working with operations that might produce missing values. Next, we'll perform addition between our initial series SIR and the newly created SIR2. This operation leverages pandas' capacity to align the indices of both series automatically. By applying the plus operator, we add the corresponding elements from SIR and SIR2, resulting in a new series stored in resultAdd_Series. This computed series consists of the sums from each aligned index, which will make it clear to see how pandas manages arithmetic operations through index alignment. Finally, we print the result to see the new series with its associated indices and values, illustrating how seamlessly arithmetic operations can be performed between two series in pandas. Next, let's see how we can implement addition between two pandas series using a method provided by the library. Instead of relying on the plus operator, we can utilize the add method from the PD_Series class. In our example, we set resultAdd method to the output of calling SIR add SIR2. This instruction takes our previously defined SIR and the new series SIR2, adds their corresponding elements together, and stores the result in resultAdd method. When we print resultAdd method, we will notice that the output is the same as when we use the plus operator. This showcases how methods in pandas maintain the same functionality as built-in operators, while also providing additional features and flexibility. This approach may be particularly beneficial when handling complex data operations or managing missing data effectively, such as when using the fill value parameter with the add method, which we will explore further. Understanding this method is crucial as it reinforces our grasp of series operations and prepares us for more advanced data manipulation techniques. Now let's take a look at how we can handle missing data using the fill value parameter in the methods of pandas series. In this example, we create two series. SIR1 contains 3 numerical values, while SIR2 has a missing entry represented by PD_NA. This setup is common in data analysis, where missing values can disrupt calculations. We can utilize the add method of the series to perform addition between SIR1 and SIR2, while the fill value parameter is set to 0. This means that whenever there's a missing entry in SIR2, it will be treated as 0 during the addition operation, instead of resulting in a missing value in the output. When we run the addition, the corresponding values from both series are summed, and you will observe that for the entry in SIR2 where the value was missing, the operation defaults to 0, ensuring the result remains complete. Consequently, the output will show the sum for each index, effectively managing any gaps in the data with ease. This feature is incredibly valuable for maintaining integrity in data analysis, especially when missing entries are the norm. Now let's take a look at how pandas handles arithmetic operations between series objects that may not align perfectly. In this example, we create a new series, SIR3, containing two values 2 and 4 and specify the data type as int64D type. When we proceed to add SIR and SIR3, pandas attempts to align the indices of both series and perform the addition. The first element of SIR, which is 0, is added to the first element of SIR3, resulting in 2. Similarly, the second element of SIR, which is 1, is added to the second element of SIR3, which is 4, yielding a sum of 5. However, since SIR3 does not provide a corresponding entry for the third index of SIR, pandas fills this position with NA, indicating a missing value. This illustrates the importance of index alignment in pandas. While it may seem straightforward to add two series, mismatched indices lead to nuanced results, such as the introduction of no values where data is absent. This mechanism enables robust handling of data, making pandas a powerful tool for data manipulation. To summarize what we've covered so far, we have explored the basic arithmetic operations you can perform on pandas series, including addition, subtraction, multiplication, and division. We have also delved into more structured approaches using pandas methods for these operations, particularly focusing on how series indices align, which is essential when operating on multiple series. As we wrap up, you will find that the principles learned with PD.Series also seamlessly apply to PD.DataFrame as well. The arithmetic rules remain fundamentally the same, just applied in a two-dimensional context. In our next session, we'll take a deeper look into pandas.Frames and how we can perform similar arithmetic operations in the world of multidimensional data. Remember, understanding series is your gateway to mastering DataFrames. So keep practicing these concepts, and you'll find yourself maneuvering pandas with ease in no time. In today's lesson, we will focus on aggregations using pandas' powerful PD.Series. Ag function, a powerful tool for performing multiple aggregations on your data with ease. This will help you summarize and make sense of your data quickly. So far, we learned about basic arithmetic operations using pandas' PD.Series, including addition, subtraction, multiplication, and division. We also explored how to create a pandas series, the significance of index alignment during operations between series, and advanced methods for performing arithmetic with consideration for missing values. Understanding these operations with series serves as a foundation for working with pandas.Frames, where similar principles apply. Now we will dive into aggregations, specifically looking at how to use the ag function to extract valuable insights from your data. Now let's see how we can create a simple pandas series to represent sales data for a small company over a week. We start by importing the pandas library, which is essential for data manipulation and analysis in Python. The sales data is then represented as a pandas series, with numerical values indicating daily sales figures for 7 days. By utilizing the PD.Series function, we pass a list of sales amounts 250, 300, 150, 400, 350, 450, and 500 to create our series. This gives us a structured format that maintains both the values and their corresponding indices, representing the days of the week. To visualize this data, we employ the print function to output the sales data, which displays each value along with its index. This output not only confirms the successful creation of our series, but also provides clarity on daily sales performance, setting the stage for further aggregation. With this series in hand, we can delve into applying aggregation functions to summarize this sales data effectively, extracting total, average, and maximum sales figures in subsequent steps. Now let's take a look at how we can implement the ag method to perform various aggregation functions on our sales data. By calling sales data ag sum mean max, we are asking pandas to calculate the total sales, the average sales, and the highest sales in a single operation all at once. This not only streamlines our code, but also provides a concise insight into our dataset. The output will showcase 3 critical metrics: the sum of sales over the week, which is provided as 2,400, reflecting the total revenue generated; the mean, which gives us an average of approximately 342.86, indicating the typical daily sales; and the maximum sales recorded in a day, which stands at 500. This quick aggregation effectively summarizes our sales performance, offering valuable insights without necessitating a detailed review of each individual entry. The ag function stands out here by simplifying the process of calculating multiple statistics concurrently, thus enhancing both efficiency and clarity in data analysis. Now let's implement the following custom aggregation function to calculate the range of our sales data. The function calculateRangeSeries takes a pandas series as input and returns the difference between the maximum and minimum values within that series. This allows us to assess the variability in our sales figures. Next, we apply this custom function alongside built-in aggregation functions using the ag method on our sales data series. By passing a list containing sum, mean, and our calculateRange function to ag, we can simultaneously compute the total sales, average sales, and the sales range. This demonstrates the flexibility of ag, as it can accommodate both built-in and user-defined functions in a single call, enabling us to gain deeper insights from our data. Finally, when we print the aggregated custom variable, we see the total sales of 2,400, the average sales per day is approximately 342.86, and the calculated range of sales is 350. This approach highlights how custom aggregation can enhance our data analysis capabilities, providing a tailored summary of the sales performance. Now let's see how we can implement a data frame using the pandas library to manage our sales data. First, we create a dictionary named data that organizes our sales entries into 3 categories: category, sales, and region. Each of these keys is associated with a list that contains relevant information. For instance, category includes types like electronics, clothing, and home, while sales provides the corresponding sales figures and region reflects the geographical area of sales. With this dictionary ready, we pass it to PD DataFrame to construct our DataFrame DF, which we then print to explore its structure. Next, we want to analyze the sales by category. To achieve this, we use the groupby function on our DataFrame, grouping the data by category. After that, we apply the agg method to calculate the total sum and average mean sales for each category. This not only summarizes our data efficiently, but also allows us to draw insightful conclusions about which categories perform best, providing a clear view at a glance without combing through all individual rows. Finally, we print the result to visualize how the categories stack up against each other in terms of sales metrics. Now let's see how we can implement aggregations using multiple columns in our data frame. By utilizing the groupby method, we can group the data by both category and region, allowing us to examine our sales data from multiple dimensions. We then follow this with the agg function, passing a dictionary that specifies which aggregations we want to apply to the sales column, specifically the total sum and the average sales. This approach will generate a neatly organized data frame summarizing total and average sales for each category in each region, providing clear insights into how different categories perform across various regions. With this aggregated view, we can quickly identify trends and patterns in sales data, revealing valuable information that can drive business decisions. It effectively transforms a complex dataset into a simpler, more comprehensible format for analysis, and it highlights the importance of multidimensional aggregation in understanding the underlying data. Now let's see how we can implement more complex aggregations using the groupby method along with the agg function in pandas. In the following code, we are grouping our data frame by both category and region, which allows us to segment our sales data into more granular insights. Specifically, we want to aggregate the sales column using both the sum and mean functions, enabling us to understand total sales as well as the average sales for each category within each region. Additionally, we also want to count the number of entries for each category per region. This is achieved by mapping the category column to the count function. The resulting data frame provides a comprehensive view of the sales performance, including total and average sales, alongside the number of entries for each category-region combination. This structured format allows for quick interpretation of how well each category is performing in different regions, providing valuable insights for business analysis. The aggregation results will enlighten stakeholders on both the performance and coverage of the sales data across various categories and regions. Now let's implement the following example to demonstrate how the agg function can handle missing values. In this code, we first introduce a missing value to our sales data by setting one of the entries in the sales column to none. This step simulates a common scenario in real-world datasets where data might be incomplete. Next, to deal with this missing value, we use the fillna0 function, which replaces any missing values with 0 before we proceed to apply aggregations. This is crucial because it ensures our calculations are not skewed by the absence of data. We then call the agg function on the updated sales column, using the aggregation functions sum and mean. This means we will calculate the total sales and the average sales while treating the missing entry as if it were 0. When we print the result, we can observe how our sum and mean accurately reflect the adjusted dataset. This approach not only allows us to summarize our sales data effectively, but also helps maintain the integrity of our analysis, ensuring that missing values do not hinder our understanding of the overall data trends. As we wrap up this exploration, it's clear that the pandas.Series agg function provides a powerful means of summarizing and extracting information from your data. Whether you are aggregating a single series, employing custom functions, or using it in multidimensional data frames, this function equips you with the necessary tools to analyze your datasets efficiently. Going forward, you can employ these aggregation techniques in your projects to pull out meaningful insights from your data, ultimately allowing for better informed decision-making in various contexts. So remember, aggregating data is not just about crunching numbers, it's about transforming those numbers into insights that can lead to action. So go forth and start aggregating your data like a pro, and who knows, maybe you'll find the next big trend just waiting for you to uncover it. Now let's see how we can implement the creation of a pandas series filled with integers. We start by importing the pandas library, which provides data manipulation capabilities. After that, we define a new series named numbers, initialized with a list of integers ranging from 1 to 5. This series will serve as our example dataset, representing a simple collection of numerical values. Next, we will write the following code to utilize the map function for transforming these integers. We'll use a lambda function to square each number within the numbers series. The map function is particularly efficient for this purpose, as it applies the specified transformation to each individual element. So when we call numbers, map lambda x asterisk asterisk 2, each number in our series will be squared, and it will return a new series called squared numbers containing these squared values. Finally, using print squared numbers will display the output, allowing us to see the results of our transformation. Each integer from the original series will now be replaced by its square, showcasing the effectiveness of the map function in handling element-wise operations efficiently within pandas. Now let's take a look at how we can use the map function to standardize categorical data, specifically fruit names, in our pandas series. We start by creating a series that contains a list of fruit names such as apple, banana, cherry, and date. This provides us with a collection of text data that we can manipulate. Next, we utilize the map function in conjunction with a lambda function, which is a concise way to apply a transformation to each element of our series. In this case, the lambda function is defined as lambda x upper, which converts each fruit name to uppercase. As we apply this function to our fruits series, the result is stored in a new variable called uppercase fruits. When we print this variable, we can observe that all fruit names have been successfully transformed to their uppercase equivalents, highlighting how map facilitates this transformation with ease. This demonstrates the strength of the map function for performing element-wise operations, making it a powerful tool for data cleaning and consistency. By ensuring that our categorical data is standardized, we set a solid foundation for any further analysis or manipulation we might perform on these values. Now let's take a look at how to create a data frame that holds our sales data. We begin by defining a dictionary named data that contains product names, quantities sold, and prices per unit. By utilizing the PD DataFrame function, we convert this dictionary into a structured data frame called salesDF. This data frame organizes our data into rows and columns, making it much easier to manipulate and analyze. Next, we want to compute the total sales for each product, and to do so, we will employ the apply function. This method allows us to execute a function along the specified axis of the data frame. We apply a lambda function that takes each row as input and multiplies the quantity by the price per unit, achieving our goal of calculating the total sales for each product. After executing this operation, we assign the results to a new column titled Total Sales. Finally, we print the updated data frame, which now includes the calculated total sales for each product row, demonstrating a practical and effective use of the apply method in pandas for row-wise operations. Now let's see how we can implement a function to categorize products based on their total sales. We start by calculating the total sales for each product by multiplying the quantity sold by the price per unit. This is accomplished using the apply function, which allows us to operate across the data frame rows. The lambda function within apply takes each row as input, accesses the relevant columns, and performs the multiplication to derive the total sales, which is then stored in a new column called total sales. Next, we want to classify these total sales values into meaningful categories. To achieve this, we define a function named categorize sales. Within this function, we establish a basic conditional logic that checks if the sales amount is greater than 300. If it is, the product is labeled as high, otherwise it receives the label low. After defining this function, we use apply, again on the total sales column, applying our categorization function to each total sales value. The results are stored in a new column called sales category. By implementing this logic, we enhance the dataset's interpretability, enabling clearer insights into the performance of our products based on their sales figures. Next, we will implement an example that demonstrates how the map function can be used with a pandas series that contains missing values. We start by creating a series called data with nan, which consists of some integers and a none value that signifies a missing entry. This setup mimics real-world data scenarios where datasets often contain none values. Now let's see how we can apply the map method to transform the elements of this series by squaring them. The lambda function lambda x asterisk asterisk 2 is used to perform the squaring operation on each element individually. When we call map with this function, it processes the series element-wise while preserving any missing values. As a result, the output we receive includes squared numbers for the valid entries, and importantly, the NaN remains unchanged. This example illustrates the robustness of map, showing its ability to handle missing data gracefully while performing straightforward transformations. Understanding how to manage NaN values during such operations ensures that your data processing remains accurate and meaningful, which is crucial in practical data analysis. To sum it up, both map and apply serve as invaluable tools in your pandas toolbox. Understanding their strengths allows you to optimize your data transformation processes effectively. You can think of map as your utility belt for quick one-to-one transformations, while apply is your Swiss Army knife for more complex row and column-based operations. Employing these methods thoughtfully can significantly enhance your ability to manipulate and analyze data, leading to more insightful discoveries and clearer presentations of your findings. And as you embrace these tools, remember, the clearer your code, the easier it is to maintain and communicate with others. We've covered a lot in this lesson, from basic transformations with map to more intricate applications with apply, demonstrating how to create and manipulate datasets efficiently. Now that you're equipped with these techniques, go out there and start transforming your data like a pro. Happy coding. Visualization is a critical component in exploratory data analysis, as well as presentations and applications. It's the tool we use to transform complex data into easy-to-understand graphical formats, making patterns, trends, and insights readily accessible. In this video, we will embark on a journey through the fascinating world of data visualization, covering its importance, techniques, and best practices that every aspiring data scientist should know. So far, we learned about the importance of the map and apply methods in pandas for data manipulation. We explored how map allows for straightforward element-wise transformations, while apply provides flexibility for more complex operations across data frames. Additionally, we discussed the use of both methods for aggregation and categorization of data, highlighting their efficiency and the handling of missing values. Equipped with these techniques, you can enhance your data processing skills and create more insightful analyses. Now, we will cover the fundamentals of data visualization, exploring why it's crucial in data analysis and how to implement it using Python. Let's begin by discussing why data visualization is so significant. With the vast amounts of data we encounter, presenting it in a clear manner is necessary for effective decision-making. Imagine trying to understand sales data spanning several years without any visual aid. It would be akin to searching for a needle in a haystack. Data visualization helps us make sense of large volumes of data and can reveal insights that might not be immediately evident through raw numbers alone. It creates a visual toolset for data interpretation and allows stakeholders to grasp complex information quickly. Next, we will delve into some foundational libraries in Python used for creating visualizations, specifically Matplotlib and Seaborn. Now let's see how we can implement a simple line plot using Matplotlib to visualize sales data over a year. First, we begin by importing the pyplot module from the Matplotlib library, which provides a convenient interface for plotting. We then define our data by creating two lists, one for the months of the year and another for corresponding sales figures. This structured data will serve as the foundation for our plot. Next, we use the pltplot function to generate the line graph, where we specify the months on the x-axis and sales on the y-axis. We enhance our visualization by adding circular markers at each data point to clearly depict sales figures for each month. To make our chart informative, we include a title with plttitle and label the axes using pltxlabel and pltlabel, respectively. Finally, we enable a grid with grid true for better readability of the graph, and we call pltshow to display the finished plot. This line plot effectively communicates sales trends over the year, providing viewers with immediate insights into the data. Now let's see how we can visualize our sales data as a bar plot using Seaborn, which builds on the capabilities of Matplotlib. First, we need to import the necessary libraries Seaborn and Pandas, allowing us to create visually appealing and informative graphics that are easy to manipulate. Next, we create a Pandas DataFrame to hold our monthly sales data, organizing it into two columns, one for the months and another for the sales figures. This structure is crucial as it enables seamless integration with Seaborn functions. Now let's write the bar plot using SNS, bar plot, specifying the x and y axes as months and sales, respectively. This function automatically computes the mean sales value for each month, which is especially helpful if we have multiple entries for any month. To enhance the visual appeal, we apply a color palette using the Viridies option, giving our chart vibrancy and clarity. Finally, we complement the visualization with title and axis labels, along with applying a rotation to the x-axis labels for better readability. Once executed, this code will provide a clear graphical representation of our sales data, making it easy to compare monthly performance at a glance. Next, we will implement a pie chart to visualize the market share distribution among several companies, which is a great way to represent categorical data. First, we define our sample data with a list of company labels and their corresponding market share sizes. The pltPie function is then used to create the pie chart, where we pass in the sizes and labels, allowing each segment to be labeled appropriately. We utilize the autopt parameter to format the percentage labels displayed on the pie slices, which provides a clear understanding of each company's market share in relation to the whole. Setting the start angle to 140 ensures that the pie chart is rotated for better visual appeal. Additionally, the pltAxis equal function guarantees that the pie chart maintains a circular shape rather than an oval. To conclude the visualization, we add a title using pltTitle, which enhances the chart's context. Finally, we call pltShow to render the chart in a window, allowing us to examine the visual representation of the market share distribution effectively. This method neatly encapsulates how categorical comparisons can be effectively communicated. Now let's implement the following scatter plot to analyze the relationship between advertising spend and sales revenue. In this code, we start by defining two lists, advertising spend and sales revenue, which contain the respective values for our variables. We use the pltScatter function from matplotlib to create a scatter plot, with the advertising spend on the x-axis and sales revenue on the y-axis. The color parameter specifies the color of the markers, while the S parameter controls their size, making them uniform for clarity in visualization. We then enhance our plot by adding a title with pltTitle to convey the purpose of the graph, and we label both axes using pltXLabel and pltILabel, ensuring that viewers can easily interpret the data. To improve readability, a grid is added with pltGridTrue, which makes it easier to gauge values on the plot. Finally, we call pltShow to render the scatter plot. This visualization effectively illustrates any potential correlation between our variables, providing valuable insights at a glance. Now let's see how we can visualize quarterly sales data over a 2-year period using matplotlib. We begin by defining two lists, quarters, which represents the time intervals from Q1 2021 to Q4 2022, and quarterly sales, which contains the corresponding sales figures for each quarter. This setup lays a solid foundation for our visualization by structuring our data effectively. Next, we utilize the pltPlot function to create a line chart specifying the quarters on the x-axis and quarterly sales on the y-axis. By adding a marker style and color, we enhance the visual clarity of our line, making it easier to identify each data point. The chart is further refined with a title, x-axis and y-axis labels, and the x-sticks are rotated for better readability. Finally, we enable a grid for the background, which helps in visually aligning the data points and observing trends. When executed, this visualization not only displays the sales trend, but also aids stakeholders in conducting a quick analysis of performance over these quarterly intervals, making it an effective tool for decision-making. When it comes to effective data visualization, few things are as crucial as clarity and comprehension. Therefore, creating visualizations that can be interpreted instantly is key. This could mean avoiding overcrowded charts, sticking to a consistent color palette, and clearly labeling axes and legends. Another important consideration is the choice of visual elements. For example, should you use a bar chart or a line graph? This often depends on the data type, the insights you want to communicate, and your audience. Moreover, accessibility is another vital aspect. Visualizations should cater to a diverse audience, ensuring that color choices accommodate colorblindness or that alternatives, such as textures or patterns, are incorporated where necessary. Using tools like the Color Brewer website can help you find color palettes that are effective for conveying your data. To wrap up, we've explored the importance of data visualization, learned how to create various types of visualizations using Matplotlib and Seaborn, and discussed best practices to enhance your charts and graphs. These foundational skills in data visualization will empower you to present complex information in a simple form, enabling better insights and decision-making. As we journey into our next session, we will delve deeper into advanced visualization techniques and interactive plots, expanding on what you've learned today. Keeping your data visualizations engaging and informative is an ongoing pursuit, and I look forward to exploring this with you. Data is everywhere, and effectively understanding it is critical. Among the various types of data, categorical data holds a unique position as it allows us to classify and navigate through complex datasets. Today, we will explore categorical data in detail, examining its definition, how to work with it in Python, and the types of visualizations that bring clarity to this form of data. So far, we have learned about the significance of data visualization in making complex data easily understandable and facilitating effective decision-making. We explored Matplotlib and Seaborn as essential libraries for creating various types of visualizations, including line plots, bar plots, and pie charts. Additionally, we discussed the best practices for clarity and accessibility in visualizations, which enhance comprehension and cater to diverse audiences. In this lesson, we will cover categorical data, its characteristics, and how to visualize it effectively. Now let's implement the following code to create a pandas data frame that captures our categorical data on fruits in their corresponding colors. We begin by importing the pandas library, which is essential for handling and analyzing our data efficiently. We then define a dictionary named data, where each key represents a category, fruit, and color. The values associated with these keys are lists containing entries of fruits in their colors, respectively. This structured format allows us to organize the data clearly. Next, we construct a pandas data frame from this dictionary using DataFrame data. This method converts our dictionary into a tabular form, making it easy to analyze and visualize the categorical variables. Finally, we print the data frame to the console, revealing how the different categories are represented alongside their entries. By laying out this foundational structure, we set the stage for more in-depth analyses and visualizations in our exploration of categorical data. This initial step is crucial as it highlights the relationships between categories, which will enhance our subsequent visual storytelling efforts. Now let's see how we can analyze the frequency of fruit categories in our dataset using pandas. The first line of code utilizes the value counts method on the fruit column of our data frame, df, to count the occurrences of each distinct fruit. This method generates a series where the index contains the unique fruit names and the values represent the corresponding counts. By printing fruit counts, we can quickly identify the distribution of fruits in our dataset, providing valuable insights into which categories are more prevalent. Next, we will write the following code to visualize this frequency data effectively. By importing the Matplotlib pyplot library, we can create a bar chart that displays these fruit counts. The plot function is called on fruit counts with the argument kind equals bar to specify that we want a bar chart. Additionally, we customize the chart's appearance by setting the color to sky blue and adding a title and axis labels for clarity. Finally, calling plt_show renders the plot, making the data visually accessible and helping us easily compare the frequency of different fruit types in our sample. This visualization adds another layer to our analysis, allowing for a more intuitive understanding of the data. Now let's see how we can visualize the fruit distribution using a pie chart, which is particularly effective for representing proportions within categorical data. To create the pie chart, we first call the pltPie function, passing in the fruit counts we calculated earlier. The labels parameter is set to fruitCountsIndex, which assigns appropriate labels based on the fruit names we've counted. Additionally, we can enhance our visualization by using the autopt parameter, which allows us to display the percentage each fruit represents of the whole directly on the pie slices. This feature delivers valuable context to the viewers, making the information clearer at a glance. The inclusion of startangle equals 90 is used to rotate the pie chart for better aesthetics, ensuring that the first slice starts from the top, enhancing the overall appearance of the chart. To maintain a circular shape for the pie chart, we use plt_axis_equal. Following that, we set the chart's title with plt_title to clearly indicate what the chart represents. Finally, we execute plt_show to display the pie chart, enabling us to visually analyze the distribution of fruit types in our dataset effectively. Now let's see how we can analyze the distribution of fruit colors alongside their types by modifying our dataset. The first code snippet groups our data frame by both fruit and color and counts the occurrences of each combination, resulting in a new data frame named color counts. This transformation utilizes the power of the groupB function along with size and unstack, allowing us to pivot the data and visualize it in a more accessible format. By printing color counts, we gain insights into how many fruits are represented in each color, setting the stage for visual analysis. Next, we will write the following code to create a stacked bar chart that effectively visualizes this distribution. In this code, we employ the plot function with kind equals bar and stacked equals true, which gives us a clear comparative view of color distributions within each fruit category. We also customize the chart with titles and labels for clarity and use PLT legend to identify the colors in the visualization easily. This stacked bar chart not only enhances our understanding of the data, but also provides a compelling visual story regarding the relationship between fruit types and their respective colors. Now let's implement some preprocessing techniques to address missing values and inconsistencies in our categorical data. First, we create a pandas data frame from a dictionary that includes none values for some entries and variations in text formatting, such as apple versus apple. This step is critical as these inconsistencies can hinder our analysis. Next, we apply string manipulation methods to ensure uniformity across the dataset. We capitalize each fruit's name using the str_capitalize method, which standardizes the entries and makes them more suitable for analysis. Additionally, we fill any missing entries in the fruit and color columns with the string unknown using the fillna method. This fills in gaps in our data, which is essential to maintain accuracy. Finally, we count the occurrences of each normalized fruit entry with the value counts method. This provides us with a summary of the frequencies of each fruit after cleaning the data. By meticulously preprocessing our dataset, we can move forward with confidence, knowing our data is tidy and ready for insightful analysis. Now let's implement the following code to visualize the distribution of fruit colors using a violin plot. This method effectively combines aspects of box plots and density plots, allowing us to see both the central tendency and variability of the data. We begin by importing the Seaborn library, which is specifically designed for statistical data visualization. The SNS violin plot function allows us to create the violin plot with our categorical variables. In this case, we set the x-axis to represent the different fruits and the y-axis for their respective colors. By passing our prepared data frame dfnan, which we previously cleaned to ensure consistency, we can effectively display this data. The inner equals quartile argument adds quartile lines within each violin, making it easier to identify the distribution's shape and range. Finally, we set a title for our plot using PLT title to provide context for viewers. The PLT show function is called to render the plot, presenting a visually engaging representation of our categorical data. This approach not only captures the distribution of colors, but also highlights the density of color representation for each type of fruit, offering valuable insights into the data. As we wrap up our exploration of categorical data, it's important to highlight the need for clear communication when interpreting visualizations. Fluent visual storytelling hinges on your ability to present your findings effectively. Whether through bar charts, pie charts, or advanced methods like violin plots, your chosen visualization style should match the data narrative. In summary, we've learned that categorical data is fundamental to the classification and organization of information, serving as a powerful tool for analysis. We covered techniques to summarize and visualize categorical data, explored various methods such as bar charts, pie charts, and more complex visualizations like stacked bar charts and violin plots. Proficiency in handling categorical data opens the door to a wealth of analytical possibilities. As we move forward, we will delve further into more advanced topics and exploration of complex datasets filled with mixed data types. Our journey into understanding the myriad ways data can be interpreted will continue, enriching our toolset for effective data-driven decision-making. Enjoy your experience navigating the vast landscape of data analysis, and I look forward to our next session where we will tackle yet another exciting aspect of data. Continuous data is a vital concept in data analysis that represents measurable quantities and can take any value within a defined range. Today, we'll dive deep into the world of continuous data, exploring its characteristics, manipulation, and visualization techniques using Python. So far, we learned about the importance of categorical data in organizing and classifying information, distinguishing it from numerical data. We explored how to manipulate and visualize categorical data using Python libraries like pandas, matplotlib, and Seaborn, focusing on various methods such as bar charts and pie charts. Additionally, we addressed common issues in categorical data, such as missing values and inconsistencies, and emphasized the significance of clear communication in data storytelling. In the next lesson, we will advance our understanding by exploring more complex datasets and analytics techniques. Now we will cover continuous data, how to work with it effectively, and various techniques to visualize it. Continuous data is fundamentally different from categorical data because it can include any value within a range, which allows for aggregating and calculating statistics like mean, median, and variance. For instance, think of height, temperature, or time. These variables can take a wide range of values and provide a wealth of information when analyzed. Next, we will write the following code to create a pandas data frame containing our continuous variables, height and weight. First, we start by importing the pandas library, which provides powerful data manipulation capabilities. We then define a sample dataset using a dictionary where the keys represent our variable names and the values are lists containing the measurements for each individual. Now let's implement the data frame by passing this dictionary to the DataFrame function. This constructs a structured table that neatly organizes our continuous data, allowing us to analyze it efficiently. Once we create the data frame, we utilize the print function to display the data frame, which reveals the individual measurements in a tabular format. Each row corresponds to an individual, while the columns represent the variables. This setup lays the groundwork for various analyses, such as calculating central tendency measures and performing data visualizations, showcasing how we can efficiently manipulate and work with continuous data in Python. Now let's calculate some basic statistics for height and weight. To do this, we first extract the mean, median, and standard deviation for the height and weight columns within our dataset using pandas' built-in functions. The mean will give us the average height and weight, while the median will indicate the middle value when the data is sorted. The standard deviation will reveal how much variation or dispersion exists from the average. These measures will be printed, providing an immediate overview of the central tendency and spread of the data, which are crucial for understanding its characteristics. Next, we will visualize this continuous data through a scatter plot using matplotlib. In this step, we plot each individual's height on the x-axis against their weight on the y-axis. By doing this, we can visually assess the relationship between height and weight in our dataset. This visualization is essential as it allows us to spot trends and relationships intuitively, such as whether taller individuals tend to weigh more, facilitating further analytical inquiries based on visual insights. Now let's see how we can mathematically explore the relationship between height and weight using the Pearson correlation coefficient. In this code, we utilize the core method from the pandas library to calculate the correlation between the height and weight columns of our data frame. Upon executing this line, we obtain a correlation value that ranges from -1 to 1. This result allows us to interpret the strength and direction of the relationship. A value close to 1 indicates a strong positive correlation, suggesting that as height increases, weight also tends to increase. Conversely, a value near -1 would suggest a strong negative correlation. Next, we will write the following code to visualize the distribution of height data through a histogram. By using the hist function from matplotlib, we set parameters like the number of bins to group the data, along with color and edge specifications to enhance visibility. This histogram will clearly illustrate how frequently individuals fall within various height ranges, allowing us to quickly identify patterns or clusters in the data, such as whether most individuals fall within a particular height range. This form of visualization is invaluable for understanding and presenting continuous data effectively. Now let's see how we can visualize outliers in our weight dataset using a box plot. The provided code snippet uses matplotlib to create a box plot for the weight variable. The plt boxplot function is called with the weight column from the data frame, producing a visual representation of the data's distribution. The box plot showcases the interquartile range, which is the middle 50% of the data, alongside the median value indicated by a line within the box. Any data points that fall outside the whiskers of the box plot are identified as outliers. These outliers can provide crucial information, as they may indicate variability in the dataset or erroneous observations that require further analysis. Following this, we apply a log transformation to the weight variable, which is often a helpful way to stabilize variance and make the data closer to a normal distribution. We achieve this by taking the natural logarithm of each value in the weight column and storing it in a new column weight log. Finally, we visualize the distribution of the log-transformed weights with a histogram, allowing us to assess if the transformation has improved the normality of the data distribution. Now let's see how we can visualize the distribution of the height data using Seaborn. We will utilize the histplot function, which allows us to create a histogram that displays the frequency of height measurements in our dataset. By setting the KDE parameter to true, we also overlay a kernel density estimate (KDE) line on top of the histogram. This line provides a smooth approximation of the probability density function, showcasing the shape of the distribution more clearly. In the code, we first import the Seaborn library, essential for enhancing our data visualizations. The next line creates the histogram, where we specify df height as our data source. The plt title, plt xlabel, and plt ilabel functions are then employed to add informative labels and titles to our plot, ensuring it's easy to understand what the visualization represents. Finally, we call plt grid axis equals y, which adds horizontal grid lines to enhance readability, followed by plt show, which renders the plot. This combined approach helps us quickly assess the characteristics of our height data distribution, identifying any potential normality or skewness effectively. As we wrap up this exploration of continuous data, it's essential to emphasize the significance of thorough analysis and effective communication. Continuous data is foundational in statistics and data science, offering insights into the intricate relationships and characteristics of various measurements. The techniques we've covered today, from basic statistics and scatter plots to histograms, box plots, and transformations, provide a strong toolkit for understanding and visualizing continuous data. As we move forward, we will dive into more advanced topics, tackling complex datasets filled with mixed data types and honing our analytical skills. Continuous data will often play a critical role in these analyses, so being well-versed in its understanding and application will benefit us greatly. Data analysis is a journey, and I'm excited to continue exploring this ever-evolving landscape with you. Thank you for joining me today, and I look forward to our next session, where we'll tackle the fascinating world of advanced analytics techniques. In this lesson, we're diving into the fascinating world of data reshaping techniques using pandas. Reshaping your data effectively is crucial for analysis, allowing you to present it in a form that best answers your questions. So far, we've learned about continuous data and its manipulations, visualizations, and the significance of outliers. Now, we will talk about some powerful methods in pandas to reshape your data efficiently. Now let's see how we can implement the concept of concatenation in pandas to combine financial data from two different quarters. First, we start by importing the pandas library to utilize its powerful data manipulation capabilities. Next, we create two separate data frames, dfq1 and dfq, each representing financial data with columns for ticker symbols, the number of shares, and price ranges marked as low and high. The first data frame, dfq, contains data for 3 companies, while the second data frame, dfq, includes 2 common companies and 1 new addition, IBM. This lack of matching columns demonstrates pandas' flexibility in handling different data structures. Now let's concatenate these data frames using the pd_concat function, where we pass both data frames in a list and set ignore index equals true. This parameter ensures that the resulting data frame, combined df, resets the index so it runs sequentially, giving a clean look to our dataset. The output reveals how pandas stacks these data frames vertically, showcasing the unique handling of missing values by inserting none for any absent entries. This method effectively consolidates our financial data for further analysis. Now let's take a look at how to merge data frames using the pd_merge function, which is a powerful method for combining 2 datasets based on common keys. In this example, we first create a data frame called sales, which contains information about salespersons and their sales figures. We then construct a second data frame called regions, which maps each salesperson to their respective region. The merging process occurs when we execute the pd_merge function, specifying the column salesperson as the key on which to join the 2 data frames. With this operation, a new data frame named merged_df is created, which combines the sales data with the regions, enriching the dataset we have. This functionality is particularly useful when you want to analyze combined data, as it prepares a consolidated view that includes both the sales figures and the geographic context of each salesperson. Additionally, the pd_merge function provides flexibility with parameters like how, enabling different types of joins such as inner, outer, left, or right, which allows you to control the alignment of data according to your analytical needs. Now let's see how we can transform our fruit production data from a wide format into a long format using pandas. We begin by creating a data frame named fruit_df, which contains state names as one column and fruit production numbers as separate columns for each fruit type, apple, orange, and banana. This format, while informative, can be less effective for certain types of analysis that require longer layout. To reshape this data, we can use the stack function. First, we set the state column as the index of the data frame, which allows us to organize our data in a way that we can stack the fruit columns into a single column. By applying stack, we effectively collapse the data frame, converting each fruit production figure into a row corresponding to its state. After stacking, we reset the index and rename the resulting columns to state, fruit, and number grown for clarity. This long-format data frame, stored as longfruitdf, is now much more versatile for analyses such as plotting or performing group operations, where having each fruit's production data aligned under a single column greatly simplifies complications that come with multiple columns. This technique enhances our ability to visualize and manipulate data effectively. Next, we will explore how to reshape our data frame using the melt function. This function provides an intuitive approach to transform data from wide format to long format without the need to set the index first, making it especially user-friendly. Now let's implement the melt function on our fruitdf data frame. In our example, we will specify id vars equals state, indicating that the state column should remain unchanged while we melt the other columns, the fruit types. Additionally, we can customize the names of the resulting variables and values by using the parameters var name and value name. We are setting these to fruit and number grown, respectively. When we print the resulting melted df, we will notice that it contains one row for each state and fruit combination, providing a long-format view of the data. This format not only enhances readability but also makes it easier to perform further analysis or create visualizations. The flexibility of the melt function allows you to tailor your data frame to meet specific analytical needs, thereby facilitating a more effective exploration of the data. Now let's take a look at how we can reshape our data frame using the PD wide to long function, which is perfect for converting wide format data into a long format based on a specific naming convention. In our example, we start by creating a data frame named DF, which consists of widget names and their quarterly sales data across 4 quarters. The column names for the quarterly sales are labeled with a common prefix, quarter, followed by the quarter number. To reshape this data frame, we call the PD wide to long function, specifying stub names as quarter, indicating the prefix of the columns we want to reshape. The I parameter is set as widget, which identifies the unique identifier for each row, while j is given the name quarter to define the new column that will capture the quarter number. When we execute this, the resulting data frame, longdf, transforms the quarterly sales data from wide to long format, allowing for a more streamlined analysis. Finally, we use resetIndex to ensure the data frame is neatly organized for further usage or reporting. This method is particularly useful in preparing data for time series analysis, enhancing the clarity and accessibility of the dataset. Now let's implement the following code to summarize our long-format fruit production data using the PD pivot table function. This powerful function is designed to reshape data while performing aggregations, making it particularly useful for summarizing large datasets into more digestible pieces. In our case, we are creating a pivot table that organizes the total production of various fruits by state. Here, we use the longfruitdf data frame as our source, specifying the state column as the index to display each state. The fruit column becomes the new columns of the pivot table, effectively transposing the data. The values parameter is set to number grown, indicating that we wish to aggregate the counts of fruit produced. Lastly, we specify the agfunc as sum, ensuring that if multiple entries exist for a state-fruit combination, their values will be summed together. When executed, this code will print out a tidy summary table that allows for quick insight into each state's total fruit production, highlighting the strengths of utilizing pivot tables for data analysis. Now let's take a look at how to transpose our data frame using the PD DataFrame T method. Transposing a data frame is a simple yet effective way to switch rows and columns, which can enhance how we visualize or process our data. In the provided code, we start by assigning the transposed version of the fruitdf data frame to a new variable named transposedf. This operation rearranges the data such that what were previously column headers become row indices. Once we've created the transposed data frame, we print it out. This will display the fruit production data in a vertical orientation, making it easier to analyze relationships between different states and fruits at a glance. For instance, in this new structure, each fruit type appears as a column, with corresponding values showing the number grown in each state listed below. This format can be particularly useful for visualization tasks or when inputting data into functions that may expect a different arrangement. Overall, transposing the data frame is a straightforward yet powerful tool in Pandas for reshaping our data to meet specific analytical needs. As you can see, Pandas provides a versatile suite of methods for reshaping data, from concatenating and merging to stacking, melting, and pivoting. Mastery of these methods will greatly enhance your ability to prepare and analyze your datasets effectively. Remember, reshaping is not just about changing forms, but also making your data more accessible and easier to understand. Happy coding! In conclusion, today we covered numerous data reshaping techniques in pandas. Through methods such as concatenation, merging, stacking, melting, and pivoting, we learned how to transform datasets into formats that are more suitable for analysis. Next, we will explore advanced analytical techniques that can deepen our insights based on the reshaped data. When working with data in pandas, one common task you will encounter is converting data formats, specifically transforming your data frame from a wide format to a long format. This process is crucial for effectively analyzing and visualizing your data. In this lesson, we will focus on three powerful methods in pandas: PD data frame stack, PD data frame melt, and PD wide to long. These techniques allow you to reshape your data for more insightful analysis. So far, we covered various data reshaping techniques in pandas, including concatenation, merging, stacking, melting, and pivoting. These methods are essential for transforming datasets into formats that are better suited for analysis. Now we will discuss methods for converting data formats, particularly how to transition from wide to long formats. Now let's see how we can implement the transformation of our data frame from wide to long format using PD data frame stack. First, we create a dictionary containing our data with fruit names as one key and their corresponding sales for 2 years as subsequent keys. We then convert this dictionary into a pandas data frame, which is initially structured in a wide format, showing each fruit sales figures for 2019 and 2020 in separate columns. Next, we set the fruit column as the index to prepare for stacking. By applying the stack method, we effectively rearrange the data frame so that the sales data for each fruit over the 2 years transitions from columns into a long format, where each row now represents a unique observation. After stacking, we reset the index to transform it back into a column, resulting in a more user-friendly data frame with the labels fruit, year, and sales. This reshaping is vital for efficient data manipulation and analysis, enabling easier aggregation and visualization of the sales figures. Next, we will write the following code to transform our data frame using the PD melt function. This method is particularly effective for reshaping data from a wide format to a long format, which is often required for analysis and visualization tasks. In our case, we begin by specifying the original data frame DF, which contains sales data for various fruits across different years. Here, the ID vars parameter indicates the column we want to keep unchanged in this instance, the fruit column. This allows us to maintain information about the fruit while we reorganize the sales data. To identify the new column that will hold the names of the years, we utilize the var name parameter, naming it year. Similarly, the value name parameter allows us to specify that the new column containing sales figures will be labeled sales. Once the melt operation is completed, we print the resulting melted data frame. This transformation yields a tidy structure where each row represents a unique combination of fruit, year, and corresponding sales figure, making it more suitable for analytical tasks such as aggregating sales data or creating informative visualizations. Now let's see how we can implement the PD wide to long function to reshape our data frame of quarterly sales data into a long format. We start by creating a dictionary named sales data where we define our products along with their corresponding sales figures for each quarter. This structure allows us to later convert it into a data frame called DF sales, which helps organize our data in a wide format. Next, we utilize the PD wide to long function to transform this data frame into a more analyzable long format. By specifying the stubnames parameter with Q, we indicate that we're dealing with columns related to quarterly sales. The I parameter identifies the index variable, in our case, the product column, which groups the data by product type. The J parameter will hold the names of the new variable created from the quarters, while the SEP parameter clarifies the character used to separate the prefix Q from the quarter numbers. After applying the transformation, we reset the index to ensure that product is included as a standard column in the final data frame. This clean long format now enables us to easily analyze sales data across quarters, paving the way for effective time-based analysis. Each of these techniques serves a distinct purpose and can be chosen based on the specific structure of your data. Remember, transforming your data into a long format is pivotal for many analytical tasks, especially in time series analysis, and when using plotting libraries that perform better with this format. So now that we understand the different methods of converting data formats, let's take a moment to compare them. While stack is a straightforward way to stack columns into rows, it may not always give you full control over the resulting column names. On the other hand, melt offers a clear syntax for defining fixed columns and is typically easier to use. The wide to long function comes in handy when you have structured data with column names that follow particular patterns. It allows for automated conversion with specific parameters, making it useful for datasets specifically designed in a certain way. As we wrap up our discussion on methods for converting data formats, it's pertinent to remember that the power of pandas lies in its flexibility and efficiency. Each of the methods we covered has its strengths, and the capability to reshape your data is crucial for effective analysis. By leveraging these functions, you can handle diverse datasets, making your data analysis process a breeze. What's next on our journey? Well, be prepared to dive into data visualizations. We will explore how to present your analysis meaningfully, making insights shine through beautiful representations. Until then, happy coding. Merging and concatenating data frames is a vital aspect of data manipulation in Python's pandas library. Understanding how to join datasets seamlessly allows us to combine information efficiently, paving the way for more insightful analysis. So far, we learned about various methods in pandas for converting data formats, specifically focusing on transforming data frames from wide to long formats. We explored three key techniques: PD DataFrame stack, which stacks columns into rows; PD DataFrame melt, which reshapes data while specifying fixed columns; and PD wide to long, which is ideal for structured datasets with specific naming conventions. Next, we will delve into merging and concatenating data frames to learn how to combine different datasets and enhance our analytical capabilities. When working with datasets, you'll quickly find that data often resides in separate tables or data frames. Merging or concatenating these data frames allows for richer datasets that can deepen our analyses. Merging is analogous to SQL joins, allowing us to combine datasets based on common keys, while concatenating simply appends one data frame to another, whether vertically or horizontally. Now let's take a look at how to create two data frames that will enable us to merge customer data with orders. First, we import the pandas library, which is essential for data manipulation in Python. We then define a data frame named customers, containing details such as customer ID, name, and age. This structured format allows us to easily access and reference customer information. Next, we create another data frame called orders, which holds information about customer orders, including order ID, customer ID, product, and amount. Notably, both data frames share the customer ID column, which will serve as the key for merging them effectively. Now let's see how we can implement the merging of these two data frames by using the PD merge function. We specify that the merge should occur based on the customer ID column, and we set how equals inner. This inner join ensures that only those customers who have placed orders will be included in the final merged result. Upon executing this code, the output will yield a new data frame that combines customer names with their respective orders and amounts, allowing for valuable insights into customer purchasing behavior. Now let's see how we can implement an outer join with our data frames. In this example, we use the PD merge function again, but this time we set the how parameter to outer. This is crucial as it determines which records we want to include from each data frame. By using an outer join, we ensure that all records from both the customers and orders data frames are represented in the resulting data frame. When we execute the merge, any customers without corresponding orders will still appear, but their order details will be filled with none values. This approach provides a comprehensive view of our dataset, allowing us to see all customers, regardless of whether they have placed any orders. Particularly, it highlights potential gaps in our data that we might want to address. By printing the resulting outer merged DF, we can analyze the structure and completeness of our combined dataset, which enriches our understanding of the customer orders while ensuring no valuable information is lost in the merging process. This method is particularly beneficial for gaining insights into customer behavior and engagement with our offerings. Next, we will write the following code snippet to perform a left join using the PD merge function. A left join is particularly useful when you want to keep all the records from the left data frame, here the customer's data frame, while combining it with matched records from the right data frame, which in this case is the orders data frame based on the common key custom ID. As we implement this, every customer will be included in the resulting merged data frame, regardless of whether they have any associated orders. This means that if a customer has not made any purchases, the order-related columns will display none values for that customer, thus preserving all relevant customer data while allowing us to see which customers are active versus inactive. By utilizing this approach, we can conduct a more comprehensive analysis that incorporates purchasing behavior alongside customer details, enabling deeper insights into our dataset and better understanding of customer engagement. After running this code, we can examine the outcome to ensure it meets our expectations. Now let's see how we can implement the concatenation of data frames using the pd_concat function. First, we create two separate data frames, sales 2020 and sales 2021, each containing quarterly sales data for 2 different years. Each data frame is structured with a column for quarter and another for sales, ensuring we maintain a consistent format between the two. Next, we utilize the pd_concat function to stack these data frames vertically. By passing a list containing both data frames as an argument and setting the ignoindex parameter to true, we instruct pandas to reset the index in the newly created data frame called concatenated sales. This ensures that the index remains sequential and avoids any confusion from overlapping indices. When executed, this code combines the sales figures from both years, giving us a single data frame with all the sales data piled on top of one another. This method is particularly valuable for quickly merging similar datasets without needing common keys, ultimately providing a more comprehensive view of the sales data across quarters. Now let's see how we can implement the concatenation of two data frames side by side. In this example, we are combining the sales figures for 2 different years, 2020 and 2021, into a single data frame. By using the pd_concat function and setting the axis parameter to 1, we specify that we want to concatenate the data frames horizontally rather than vertically. This method enables you to combine the data in such a way that each year's sales figures will appear in distinct columns adjacent to one another. Additionally, the output will provide a comprehensive view of both years' sales for easier comparison and analysis. This technique is particularly useful for visualizing changes in sales figures over time, as it permits an immediate side-by-side comparison. Once executed, the printed data frame will reveal how the sales data for both years aligns, facilitating deeper insights and understanding of trends in sales performance. This approach not only augments the clarity of our analysis, but also enhances our ability to derive actionable insights from the data at hand. Handling axis alignment can sometimes be tricky, especially if the two data frames have different indices. To manage this, you can use the join parameter in the pd_concat function, allowing you to specify how to handle non-matching indices. If you encounter situations where you'd prefer to keep all indices regardless of matches, you could set join equals outer. Alternatively, if you only want to keep the intersection of indices, setting join equals inner would suffice. This flexibility ensures your concatenation suits your specific analytical needs. Now that you're familiar with merging and concatenating data frames, it's essential to recognize the scenarios where each is best applied. Merging is best when you have related information spread across different data frames and need to combine them based on common keys. On the other hand, concatenation is ideal when stacking similar datasets or side-by-side comparisons are required without the need for key relationships. To wrap things up, mastering merging and concatenating in pandas equips you with powerful tools for data manipulation. Whether you're unifying disparate datasets with merges or simply stacking data frames together with concatenation, these techniques significantly enrich your data analysis workflow. As you proceed with your data analysis journey, remember that the ability to combine data frames efficiently is crucial for creating comprehensive insights. As always, practice makes perfect, so don't hesitate to experiment with merging and concatenating various data frames to see how they interact. Happy coding, and let's look forward to diving into the wonderful world of data visualizations in our next lesson. Now let's dive into the world of group by operations in pandas, one of the most powerful features for data analysis. In this session, we will explore how to efficiently summarize and aggregate data based on specific criteria, giving us insights that are crucial for strategic decision-making in any field. So far, we covered how to merge and concatenate data frames in pandas, building a foundation for efficient data manipulation. We learned about the pd_merge function for combining datasets based on common keys and explored various types of joins, including inner, outer, left, and right. Furthermore, we discussed the use of pd_concat for stacking and comparing data frames side by side, emphasizing scenarios for each technique. These skills enhance our analytical capabilities and prepare us for more complex data visualizations in future lessons. Now we will talk about group by operations, a key technique to glean insights from data by segmenting it into groups based on one or more columns. This method allows us to perform calculations on each group independently, which is efficient and enhances our data analysis. Now let's create a sample pandas data frame that simulates sales data for widgets sold across different regions and months. This data frame will serve as the foundation for our group by operations. To define the data frame, we use the PD data frame constructor, passing in a list of lists where each inner list represents a row of data. The columns include region, widget, month, sales, and returns, which provide a structured way to analyze the sales-related metrics for each widget. Next, we specify the column names using the columns parameter to ensure our data frame is easy to read and understand. This structured representation allows us to later perform aggregations based on these criteria. By analyzing this data frame, we can apply various group by operations that will enable us to derive insights into sales performance and returns, which are crucial for effective decision-making in business. Importantly, this foundational step prepares us for more complex aggregations and further analysis as we delve deeper into the capabilities of pandas. Now let's take a look at how to summarize sales and returns data for each widget using a straightforward group by operation. The code snippet begins by grouping the data frame by the widget column and immediately applying the sum function to aggregate all numeric columns. This operation yields a new data frame where each row represents a unique widget, and the corresponding summed values for sales and returns are displayed. However, it's important to note that this approach will also sum any string columns, like region and month, resulting in concatenated string outputs which might not be desirable. To enhance our analysis, we can refine this by explicitly specifying only the columns we wish to aggregate. By selecting the sales and returns columns and applying the aggregate function, we ensure our results focus solely on the data we care about. This not only prevents unwanted summations of string values but also streamlines our output, making it easier to interpret the total sales and returns for each widget. Implementing this targeted aggregation approach improves both performance and clarity in our data analysis tasks. Now let's see how we can enhance our aggregation results using the PD named Ag class. This approach allows us to provide more descriptive names for the output of our aggregation, making the resulting data frame easier to interpret. In this code, we begin by grouping the data frame by the widget column and applying the aggregation function, ag, to compute totals. We specify the aggregations explicitly by using PD named ag, which requires the name we want to assign to the aggregated result in the corresponding column to aggregate. For example, we calculate the total sales and total returns, renaming them to sales total and returns total, respectively. This ensures that the output column names are clear and reflective of their content. Upon executing this code, the result will be a data frame that displays the total sales and total returns for each widget, with the descriptive column names enhancing clarity. This usage of PD named ag is particularly beneficial when dealing with larger datasets or aggregating multiple columns, because it analyzes and labels the data in a way that is easy to comprehend and interpret. Now let's see how we can implement a more advanced grouping operation by considering multiple criteria at once. Here, we will group our sales data not only by the type of widget, but also by the region in which they were sold. This dual grouping allows us to obtain a more granular view of the data, providing insights into both widget performance and regional differences. In the code, we initiate the GroupB method on our data frame, passing a list with both widget and region as the grouping columns. We then utilize the ag function with PD named ag to specify the aggregations we want to perform on the sales and returns columns. Specifically, we will calculate the total sales and total returns for each combination of widget and region. Upon running this code, we receive a multi-index data frame that succinctly summarizes the results. Each row signifies a specific widget region combination, with the total sales and returns clearly labeled. This format not only enhances our understanding of sales distribution across regions, but also supports more sophisticated analyses, making our findings far more actionable. Overall, this approach exemplifies the power of pandas in handling complex data aggregations effectively. Now let's see how we can implement a more comprehensive aggregation using pandas. In this code snippet, we extend our previous aggregations to not only calculate the total sales and returns for each widget grouped by region, but also to determine the minimum sales and returns values. We achieve this by utilizing the GroupB method on our data frame, specifying both the widget and region columns as our primary grouping criteria. Following this, we leverage the ag function, which allows us to apply multiple aggregation functions simultaneously, enhancing the depth of our analysis. By using PD named Ag, we can clearly label the results for better readability. Here we define sales total and returns total to represent the total sales and returns, calculated using the sum function. Furthermore, we introduce salesmin and returnsmin, which will compute the minimum sales and returns respectively using the min function. When we run this code, it will produce a data frame that not only summarizes the total figures, but also provides insights into the minimum performance metrics for each combination of widget and region, facilitating a more detailed evaluation of our data. Now let's implement a custom aggregation function to enhance our analysis capabilities. Here, we define a function named customaverage, which calculates the average of a series of numbers. It checks if the length of the series is greater than 0 to avoid division by 0, returning the sum of the series divided by its length if it is, and 0 otherwise. Next, we will apply this custom function to our data frame grouped by the widget column. We use the ag method along with PD named ag to create a new aggregated column called custom AVG, which will store the results of our custom aggregation. This allows for precise control over the calculations performed on our grouped data. By leveraging this flexibility, we can derive metrics that go beyond the built-in functions, such as calculating a weighted average of sales instead of simply summing them up. The output will provide insights tailored to specific analytical needs, enhancing the overall capability of our data workflow and ensuring that the aggregated results are aligned with the unique requirements of our analysis. As we start wrapping up our exploration of group by operations, it's significant to remember the importance of documentation and testing your code. When we work with pandas and group by functions, it's easy to overlook that operations can yield unexpected shapes or formats, especially with custom aggregations. Always double-check your grouped outputs. Make sure the indexes and column labels match your expectations. This makes your data manipulation not only effective but also transparent and maintainable. In conclusion, mastering group by operations opens up a wealth of opportunities for insightful data analysis. With the knowledge of how to segment your data, manipulate it, and extract meaningful metrics, you're well on your way to becoming proficient in pandas. So far, we've learned how to leverage group by operations in pandas for powerful data analysis. We discussed the fundamental concepts, executed basic aggregations, customized results with named aggregations, and even experimented with custom functions. In our next sessions, we will delve deeper into more complex data transformations and visualizations that can lead to richer insights and more effective communication of data findings. Keep practicing and happy coding. Data aggregation in pandas is a powerhouse skill for any data analyst. It allows us to summarize, compute, and manipulate our datasets to derive valuable insights. Today, we're diving deep into techniques for data aggregation and exploring how to use these techniques efficiently with the AG method in pandas so you can harness the full potential of your data. So far, we have learned about merging and concatenating data frames in pandas, exploring tools like PD merge and PD concat for effective data manipulation. We built a solid foundation for handling data efficiently and prepared ourselves for advanced data analysis through group by operations. We discussed how to segment data into groups, perform calculations, and customize results using named aggregations. Now we will amplify our understanding by delving into the various techniques for data aggregation, focusing on the AG method to enhance your analytical capabilities. Now let's see how we can implement the grouping and aggregation of our sales data. We start by creating a data frame from a dictionary that contains sales data grouped by region, along with corresponding sales and returns values. This will serve as our dataset for analysis. Next, we will group this data frame by the region column using the groupby method. This operation segments our data into two groups, north and south, allowing us to analyze the performance within each region. To aggregate the total sales and returns for each of these groups efficiently, we will use the AG method. This method allows us to define multiple aggregation functions applied to specified columns. In our case, we'll use PD. Named AG to sum up both the sales and returns columns, renaming the output columns to total sales and total returns for clarity. Upon execution, the resulting data frame will provide a concise summary of total sales and returns for each region, facilitating easier interpretation and insight generation from our data. This demonstrates the power of aggregation methods to summarize and analyze grouped data efficiently in pandas. Now let's see how we can implement multiple aggregation functions simultaneously using the AG method. In the code, we are grouping the data by the region column and applying several aggregation functions to the sales and returns columns. By utilizing PD named ag, we can specify custom names for our aggregate results, which enhances the clarity of our output data frame. We calculate not only the total sales and total returns for each region, but also their averages. This allows us to gain deeper insights into sales performance and returning trends for each region in a single, concise output. The result will present a data frame that details not just totals but averages, enabling a more comprehensive analysis of the data. This method not only streamlines the aggregation process, reducing the need for multiple groupie calls, but also provides a clearer picture of the data at a glance. Analyzing these outputs can offer strategic insights for decision-making, particularly in identifying areas that require attention in customer satisfaction and operational efficiencies. Now let's see how we can implement a custom aggregation function to apply a discount on total sales. We begin by defining the apply discount function, which accepts a total sales figure and reduces it by a discount rate of 10%. This is achieved by multiplying the total by 1 minus the discount rate, which returns the discounted total. Next, we can utilize this custom function within a group by operation on the data frame. We group the data by the region column and apply our discount function to the sales column using the AG method, naming the output as discounted total sales. This allows us to see how total sales might be adjusted for business practices like discounts, thereby offering a more accurate reflection of revenue. When we print the results, we can observe the new discounted sales figures for each region, giving us valuable insights into actual revenue after applying the discount. Using custom functions like this enables you to tailor your data analysis to fit specific business models and logic, enhancing your analytical capabilities within Pandas. Now let's enhance our data frame by including additional product information along with the sales data. We'll be grouping our dataset not only by region but also by product to extract insights across these dimensions. First, we define a dictionary, sales data, which contains our sales records including region, product, sales, and returns. By passing this dictionary to PD DataFrame, we create a DataFrame DF that organizes our data in a structured format. Next, we will implement the grouping operation using the groupby method on our data frame. Here we'll specify both region and product as the columns by which we want to group our data. This allows us to analyze the aggregated sales figures and return rates within each combination of region and product. We will utilize the AG method for aggregation, where we will calculate total sales and returns with meaningful column names using PD named AG. Finally, printing the result will reveal a detailed breakdown, showcasing total sales and return counts for each product within each region. This approach unveils trends that might be obscured when analyzing the data under a singular dimension. Now let's see how we can implement multiple aggregation functions to provide a deeper insight into our sales and returns data. In this example, we group the data frame by both region and product to calculate not only the total sales but also the average sales and the count of returns for each combination of region and product. Such detailed aggregation allows us to analyze different dimensions of our data simultaneously. We begin by using the groupby method to segment our data frame based on region and product. Following this, we apply the AG method to gather multiple results. We sum the sales for each category with total sales, compute the average sales with average sales, and count how many returns occurred with count returns. Each of these computations provides specific metrics that help us understand overall performance and demand patterns. The output reveals not just the totals and averages, but also the frequency of returns, offering insights that can inform operational changes, such as product strategy or inventory management. This multifaceted view of the data empowers stakeholders to make more informed decisions based on performance metrics across both regions and products. In sum, aggregation in Pandas is a powerful feature that enables you to derive meaningful insights from your data with elegance and efficiency. By using the AG method, you can customize your analyses, apply multiple calculations simultaneously, and even define your functions as necessary. This flexibility permits you to analyze data from numerous perspectives and ultimately enhances the value derived from your analyses. The techniques learned today aren't only about numbers, they're about telling a story with your data. As you implement these aggregation techniques in your work, remember that understanding the context of your numbers can lead to smarter business decisions and strategies. Data is undoubtedly powerful, but it's your analysis and the questions you ask that bring it to life. As we wrap up today's lesson, take a moment to reflect on these aggregation techniques, practice using them in your own analyses, and explore some custom functions tailored to your project's needs. With these data aggregation techniques under your belt, you're well prepared to leverage pandas for the most effective data storytelling possible. Until next time, happy analyzing. As we dive into advanced applications of the pandas group by functionality, prepare to enhance your data wrangling toolkit even further. Understanding how to effectively group and analyze your data can lead to more insightful interpretations, enabling you to evaluate records more fairly within diverse cohorts. So far, we learned about the powerful data aggregation capabilities in pandas, focusing on the AG method that allows for efficient analysis of datasets. We explored techniques for grouping data, applying multiple aggregation functions, and even creating custom functions to meet specific analytical needs. We also discussed the significance of segmenting data by multiple attributes to unveil deeper insights. As we move forward, we will continue to enhance our understanding of these methods and their practical applications in data analysis. Now let's implement the code to create our initial data frame, which serves as the foundation for our group by operations. We start by importing the pandas library, a powerful tool for data manipulation. We define our data as a dictionary containing sales information with columns for region, product, sales, and returns. This structure allows us to view sales patterns across different regions and product offerings. Once the data is established, we use the DataFrame function to convert our dictionary into a structured data frame, DF. Next, we will perform a group by operation to analyze our sales data by both region and product, which will help us in understanding the total and average sales alongside total returns for each category. By invoking the group method on our data frame and aggregating with specific functions like sum for total sales and returns and mean for average sales, we can transform our dataset into a more insightful format. Finally, we reset the index to organize the results into a clearer tabular format. The output will provide a comprehensive overview of sales performance across different product and region combinations, illuminating essential insights needed for strategic decision-making. Now let's explore how we can enhance our analysis by applying multiple aggregation functions to our group data. We start by grouping our data frame DF based on both region and product. This allows us to evaluate various metrics side by side for each unique combination, providing a comprehensive overview of our sales performance. In the aggregation function, we specify several calculations: the total sales and average sales, along with the maximum and minimum sales for each group. Additionally, we are summing up total returns. These multiple metrics will help us capture not just the cumulative sales, but also the variability within each group, highlighting extremes in performance. After aggregating, we reset the index to get a cleaner data frame layout for easier readability. When we print the result, we can observe how each region and product combination stacks up in terms of total sales, average sales, maximum and minimum sales figures, and total returns. This expanded dataset equips us with a broader view to analyze sales performance and make more informed decisions while interpreting our data insights. Now let's implement the custom aggregation function to calculate the sales range. We start by defining a function named salesRange, which takes a series of sales data as input and returns the difference between the maximum and minimum sales values. This function is particularly useful to determine the variability of sales within each group. Next, we use this function within our aggregation process by grouping the data frame DF by both region and product. In this aggregation, we calculate the total sales for each group using the built-in sum function, while we apply our salesRange function to compute the sales range for each group. Additionally, we sum the returns in the same operation. The resulting data frame, custom result, holds valuable insights, revealing how consistent or varied sales figures are across different regions and products. By analyzing this aggregation, we can identify patterns in sales fluctuations, enhancing our understanding of the data. This approach showcases how defining custom logic in aggregations can uncover insights that standard metrics might miss. Now let's implement conditional grouping to enhance our analysis by focusing only on high-performing products. We start by creating a new data frame, filtered data, that retains only those entries where sales exceed 300 units. This filtering process ensures that we are analyzing the most relevant data and excludes less significant entries that might skew our results. Next, we group this filtered data by both region and product, allowing us to aggregate the total sales and returns for each combination of these attributes. By using the AG method, we specify the calculations we want. We summarize total sales and returns, which gives us a clearer view of performance for high-selling products across different regions. This approach not only enhances focus but also streamlines our analysis, making it more efficient to identify trends and insights. The output of this operation will present a data frame that highlights the total sales and returns for each region product pair that meets our sales criteria, allowing for more informed decision-making regarding product strategies and performance evaluations. Now let's implement the following code to set up our dataset with a focus on time-based grouping. We start by creating a dictionary named data, which includes a date column converted to datatime format, along with the region, product, sales, and returns columns. This structured data is then used to form a data frame called DF, which serves as our main dataset for analysis. Next, we add a new column named month to our data frame, extracting the month from the date column. This allows us to group our data by month, facilitating a temporal analysis of sales. We then perform a group by operation, aggregating the total sales and returns based on both the month and region. This results in a new data frame, monthly sales, which provides a summarized view of the sales data over the defined time frame. Finally, printing monthly sales reveals the aggregated results, showcasing how different regions performed month over month. This approach not only highlights seasonal trends, but also helps organizations make data-driven decisions based on temporal purchasing behaviors. In summary, mastering the advanced applications of group by functionality in Pandas leads to a more nuanced understanding of your datasets. Whether through hierarchical indexing, custom aggregations, or conditional filtering, these techniques empower you to unveil deeper insights and draw meaningful interpretations from your data. Data is not just numbers, it's a narrative waiting to be told. Every grouping and aggregation adds another layer to that story. Embrace these advanced techniques, practice incorporating them into your real-world data analyses, and watch as your analytical capability transforms. Happy data wrangling, and I can't wait to see what insights you'll uncover next. Properly working with temporal data, dates and times, may seem straightforward at first glance, but as we delve deeper, we see how surprisingly complex it truly is. In this session, we'll unlock the intricacies of temporal data types and explore how they can significantly enhance our data management practices. So far, we learned about advanced applications of the Pandas group by functionality, enhancing our data analysis skills. We explored hierarchical indexing, allowing insights from multiple attributes, and added custom aggregation functions to tailor analyses to our needs. Additionally, we discussed conditional grouping to focus on high-performing products and the importance of time-based grouping for observing trends. These techniques empower us to uncover deeper insights and improve our data interpretation skills. Now, we will talk about temporal data types, highlighting their importance in data analysis and how to handle them efficiently using Python's Pandas library. Now let's see how we can generate a sequence of dates using Pandas. The code begins by importing the Pandas library, which is essential for handling temporal data. We then utilize the pd_dateRange function, specifying a start date and an end date to create a date range. This function is powerful as it not only allows us to generate dates systematically but also caters to various intervals, making it ideal for creating schedules or timelines. After executing this line, we use the print function to display the created date range, which would show all the dates from January 1, 2023 to January 10, 2023. Next, we will write the following code to calculate the difference in days between two specific timestamps. Here, we define the start and end dates using the pd_timestamp function. This is crucial because it ensures that our dates are treated as proper timestamp objects, allowing for accurate calculations. By subtracting the start date from the end date, we get a time delta object, which holds the duration between the two dates. Finally, we access the days attribute to retrieve the difference in days as an integer, providing a clear and straightforward insight into the duration between those two dates. Next, we will write the following code to demonstrate how we can extract specific components from a timestamp in Pandas. We start by creating a timestamp which captures both the date and time. With the timestamp established, we can easily access just the date part using the date method and the time part using the time method. This is especially useful in scenarios where we might need to perform operations with just the date for filtering data sets or require only the time component for scheduling tasks. In addition to extracting these components, it is essential to understand how to work with timestamps that are times in a way. In our next example, we will create a naive timestamp which lacks time zone information and then utilize the tzLocalize method to assign a specific time zone to it. This is crucial because converting a naive timestamp to a time zone away one prevents calculation errors that can arise when dealing with data collected from different regions, ensuring accurate temporal analyses. By making these adjustments, we enhance our ability to manage temporal data effectively. Now let's see how we can create a sequence of hourly timestamps using pandas. The first part of our code employs the pd_dateRange function to generate a date range starting from January 1, 2023. By specifying the period's parameter as 24 and the freq as h, we instruct pandas to produce 24 timestamps at an hourly frequency. This is particularly useful when gathering temporal data at regular intervals, providing a consistent timeline for our analysis. The print function then outputs the generated timestamps, allowing us to visualize the hourly intervals we have just created. Next, we will implement a simple time series dataset using the hourly timestamps we've just generated. Here, we create a pandas series initialized with a range of 24 integers, each representing a hypothetical data point corresponding to our hourly timestamps. It's important to set the index of this series to our previously generated hourly dates, as this alignment allows us to leverage the power of time series analysis. Following this, we apply the resample method to the dataset. Resampling to a daily frequency using D and calculating the mean enables us to derive daily averages from our hourly data. This technique is essential when we want to synthesize high-frequency data into a more manageable daily summary, yielding insights that are easier to interpret. Finally, we print the results to visualize these daily averages. Now let's see how we can handle missing values in our time series data. We begin by creating a date range that includes gaps in our data. This is achieved using the pd_dateRange function, which generates a sequence of dates from January 1 to January 5, 2023. We then define a pandas series named DataWithGaps, which includes some numerical values along with none to represent missing values at certain timestamps. Next, we implement the ffill method on our series. This function is key to addressing the missing data by filling in the gaps with the lost valid observation. By moving forward through the series, it propagates the most recent non-null entry to replace the none values, ensuring the integrity and continuity of our time series. Finally, we display the filled data using a print statement, which will show the completed time series with missing values effectively handled. This approach highlights how using pandas, built-in functions can simplify the management of temporal data, making analyses more robust and reliable. Now let's see how we can implement data aggregation by resampling our minute-level time series data to an hourly frequency. First, we create a date range consisting of minute-level timestamps using the pd_dateRange function, which allows us to specify the start date, the number of periods, and the frequency, in this case t for minutes. We then generate a series of values indexed by these minute timestamps, essentially simulating minute-level data. Next, we want to aggregate this data to a higher granularity, specifically to hourly data. To achieve this, we utilize the resample method, specifying h as our desired frequency. The sum function then computes the total of the minute values for each hour, providing us with a consolidated view of our data across hourly intervals. Finally, we print the hourly aggregated data to observe the results. This method of resampling is invaluable for analyzing trends and patterns, as it allows us to work with a more manageable set of data points, while retaining essential insights from our original minute-level data. Now let's implement a simple visualization to help us understand the trends in our hourly data. We begin by importing the matplotlib pyplot library, which is a powerful tool for creating static, animated, and interactive visualizations in Python. Next, we set up the figure size for our plot, making it 10 inches wide and 6 inches tall, ensuring it's visually accessible. Following this, we use the plot function to draw a line graph, where we plot the index of our hourly data on the x-axis, representing the dates, and the corresponding values on the y-axis. This graphical representation allows us to observe data trends over time effectively. To make our plot more informative, we add a title that describes the contents of the graph as hourly data trends, clearly indicating what the viewer is looking at. The x-axis is labeled date, while the y-axis is labeled values, providing context for each axis. Finally, we enable a grid on the plot to enhance readability and then display the plot using show. This visualization will help us uncover any significant patterns or anomalies that exist in our time series data, which are crucial for decision-making in various applications. To conclude, working with temporal data types might appear simple at first, but as we've explored, they present a wealth of opportunities and challenges. Mastery of these concepts not only enriches your data analysis capabilities, but also paves the way for thorough insights into time-related data patterns. With the knowledge gained here, you're now equipped to better navigate the complexities of dates and times in your data projects, ensuring that your analyses are both robust and insightful. Happy analyzing! Missing data can have an immense impact on your data analysis, but it may not always be clear when and to what extent. Today, we are going to dive deep into the world of missing data, understanding its implications, exploring various techniques for handling it, and how we can utilize the pandas library in Python to tackle these challenges effectively. So far, we learned about the complexities of temporal data types and their significance in enhancing data management and analysis. We explored the use of pandas DataTime64 data type, learned to manipulate timestamps, and delved into time zone awareness. Additionally, we discussed handling missing values, understanding granularity, and the importance of visualization in uncovering trends within temporal data. These skills empower us to effectively work with and analyze time-based datasets. Now we will cover various techniques to handle missing data, an essential skill for any data analyst. Now let's implement the following code to effectively identify missing values in our dataset. First, we import the pandas library, which is essential for data manipulation and analysis. We then create a simple dictionary named data, where we utilize two keys, day and temperature. The day key holds a list of days in a week, while the temperature key holds temperature readings, some of which are intentionally set to none to simulate missing data. Next, we construct a data frame called df with this data, allowing us to organize it into a tabular format that pandas handles efficiently. With our data frame ready, we proceed to identify any missing values by using the isNull function. This function returns a Boolean data frame indicating the presence of missing values. By chaining this with the sum function, we can summarize the total count of missing entries in each column. Finally, we utilize a print statement to output the count of missing values, which provides us with a crucial insight into the quality of our dataset. This understanding forms the foundation for the subsequent decisions on how to address these gaps effectively. Now let's see how we can implement a simple but effective method for handling missing data by using the dropna function. In our code snippet, we drop any rows from the data frame that contain missing values. This is particularly useful when the proportion of missing values is relatively low, as it helps maintain the integrity of the dataset without the complications introduced by imputation methods. By assigning the result of dropna to a new data frame called dfDropped, we ensure that our original data frame remains unchanged, allowing for flexibility and further analysis if needed. After dropping the rows, we print the modified data frame, which now excludes any entries where data was missing. It's essential to recognize that while this technique is straightforward and quick, it can lead to a loss of critical information if a significant portion of the data is excluded. Therefore, always consider the impact of this approach on your overall analysis and dataset before applying it. Now let's see how we can impute missing temperature values using the mean. First, we calculate the mean temperature from the temperature column in our data frame. This is done using the mean method, which provides us with a single value representing the average temperature of the recorded days. Once we have this mean value, we move on to filling the missing entries in the same column. To achieve this, we utilize the fillna function, which is a convenient method in pandas to replace missing values. By passing the calculated mean temperature as an argument to fillna, we instruct pandas to substitute all instances of nyan, not a number, in the temperature column with this mean value. Setting the in-place parameter to true ensures that the modifications are applied directly to the original data frame without creating a copy. After executing this line of code, we can print the updated data frame to confirm that the missing temperature values have been successfully filled in. This technique maintains the integrity of the dataset while providing a reasonable estimation in place of the gaps, which is crucial for further analysis. Now let's explore how to perform median imputation to handle missing temperature values in our dataset. The first step we take is calculating the median of the temperature column using the median function. This statistic serves as a robust measure of central tendency, especially beneficial in datasets featuring outliers or skewed distributions. Once we have the median value, we can efficiently replace any missing entries in the temperature column with this calculated median using the fillna method. By setting the in-place equals true argument, we ensure that these changes are applied directly to our existing data frame, df, rather than creating a new object. After executing this code, we can observe the updated data frame, which now showcases the data after the median imputation. This method not only helps to retain the dataset size, but also minimizes the bias that might arise from using the mean in less symmetrically distributed data. By applying median imputation, we ensure that our dataset is more representative, allowing for better analysis and interpretation of the temperature trends. Now let's implement the following technique to address missing values in our dataset using forward fill imputation. This method is particularly effective for time series data where the temporal order is crucial. In our code, we utilize the fillna function from the pandas library with the method equals ffill argument. The ffill stands for forward fill, which means that this function will take the last non-null value and use it to fill the gaps in the series. By applying inPlace equals true, we ensure that the changes are made directly to our data frame df without needing to create a new variable. This approach helps maintain continuity in the dataset, as each missing temperature value will be replaced by the most recent observed temperature prior to the gap. However, it is essential to note that while this technique is intuitively logical for time series data, it assumes that the previous value is a valid estimate for the missing entry. Therefore, careful consideration is necessary to ensure that the data is appropriate for this type of imputation. After applying forward fill, we can then print the updated data frame to observe the effect of this method on our missing temperature values. Now let's implement the following code to perform interpolation on our data frame's temperature data. The line of code ensures that any missing values in the temperature column are filled in using pandas' built-in interpolate function. This function adapts a statistical method that estimates missing entries by examining the adjacent values within the dataset, thus maintaining a degree of trend continuity. As a result, the missing temperature values will be replaced with calculated estimates based on the observed temperatures from surrounding days. Once the interpolation is executed, we print the updated data frame to visualize the changes. This allows us to see how the missing data points have been filled, providing improved continuity in the temperature readings across the week. It is essential to remember that while interpolation can yield more precise results, it is crucial to ensure that the dataset's characteristics align well with this method to avoid misleading assumptions. By employing interpolation here, we enhance the dataset's integrity and prepare it for further analysis without losing critical information. Now let's see how we can implement k-nearest neighbors, KNN, for imputing missing values in our temperature dataset. We start by importing the KNN imputer class from the Sklern impute module, which provides the functionality to impute missing values using KNN. Next, we instantiate the KNN imputer and specify the number of neighbors to consider. In this case, we set it to 2. This means the imputer will look at the 2 nearest data points to predict the missing temperature value. Once the imputer is set up, we can apply it to our data frame. Specifically, we target the temperature column, which contains the missing values. By calling the fitTransform method on this column, the imputer processes the data based on the available observations, effectively filling in any gaps with predictions derived from the nearest neighbors. After the imputation is complete, we print the updated data frame, allowing us to see the effects of the KNN imputation on our dataset. This method not only facilitates a more context-aware approach to filling in missing data, but also enhances the overall analysis by preserving the relationships in the dataset. Now we've covered a variety of techniques for handling missing data. Each method has its unique pros and cons, and the decision to use one over another should be informed by the nature of the data, the underlying patterns, and the specific analysis goals. Remember that there's no one-size-fits-all answer when it comes to missing data. The context is critical. To wrap up, it's crucial to thoroughly document how missing values are handled in any analysis, as this can affect reproducibility and comprehension when communicating results. Implementing the right techniques can significantly enhance the quality of your analysis and lead to more accurate insights, preventing the pitfalls that missing data can bring. In conclusion, understanding and managing missing data is fundamental to effective data analysis. Whether you're deleting, imputing, or employing advanced techniques, having a robust strategy will ensure you derive meaningful insights from your datasets. Embrace the challenges posed by missing data and let them guide you toward more resilience in your analysis processes. Happy analyzing! Time series analysis is a powerful tool that allows us to analyze data points collected or recorded at specific time intervals. It's a method that brings various insights to the table, especially when it comes to understanding trends, seasonality, and cyclical patterns in datasets. In this lesson, we will explore the applications of time series analysis using the Denver crime dataset, which is huge, with over 460,000 rows each marked with a data time of when the crime was reported. This will help us highlight the significance and versatility of time series analysis while diving into key concepts and techniques. So far, we have learned about the impact of missing data on analysis and the importance of recognizing it as a first step in handling datasets. We explored various techniques to manage missing values, such as deletion, mean, median, and mode imputation, along with more advanced methods like interpolation and model-based techniques. Using the pandas library, we demonstrated how to identify and fill missing values while considering the nature of the data. By applying these strategies, we can maintain dataset integrity and derive meaningful insights during analysis. Now, we will talk about the fascinating applications of time series analysis through practical examples. Now let's implement the following code to load our Denver crime dataset into a pandas data frame. We begin by importing the pandas library, a powerful tool for data manipulation in Python. The read CSV function allows us to read the CSV file named Denver crime data, CSV, and the argument parseDates equals DataTime, ensures that the DataTime column is understood as a DataTime object. This is crucial for time series analysis, as it enables us to perform operations like date filtering and aggregating data over time effectively. Once the dataset is loaded, we utilize the head method to display the first few rows of the data frame. This snapshot gives us an overview of the data structure, including the types of columns we are dealing with, such as crime type and data time, thus laying the foundation for our subsequent analyses. By understanding our dataset structure right from the start, we position ourselves to uncover significant insights through further exploration and visualization of crime trends. Now let's implement the following process to visualize our crime data over time, which is crucial for identifying trends. First, we convert the data time column in our data frame to just the date, enabling us to aggregate our crime data by day effortlessly. This step is vital as it allows for a clearer understanding of daily changes in crime rates. Next, we utilize the groupB function to count the number of crimes reported for each date. This aggregation provides us with a simplified dataset that reflects daily crime totals, helping us recognize patterns more effectively. Now we will visualize the daily crime counts using Matplotlib. We start by setting the size of the figure for our plot to make it more legible. Then we use the plot function to create a line graph, plotting the dates on the x-axis against the crime counts on the y-axis. Additionally, we add a title and labels to the axes to make the graph informative. Finally, rotating the x-axis labels ensures they are readable even if they overlap. This visualization will reveal underlying patterns, spikes, and variations in crime, crucial for deeper analysis. Now let's implement the following lines of code to ensure our daily crime counts are correctly indexed for time series analysis. First, we import the statsModels library, which is essential for decomposing our time series into meaningful components. Then we convert the index of our daily crimes data frame to a DataTime format using PD to DataTime. This step is crucial as time series functions in statsModels require a proper DataTime index to accurately analyze trends and seasonality. Next, we utilize the seasonal decompose function from the statsModels SAR module. By specifying the model type as additive, we ensure that our decomposition separates the data into three distinct components: the trend, seasonal fluctuations, and residual errors. This decomposition will provide us with clarity on how different elements contribute to crime rates over time. Finally, we generate visualizations of these components using the plot method followed by PLT_show. This not only helps us understand the individual effects of trends and seasonal variations, but also fosters deeper insights into the underlying patterns within our crime data, aiding us in investigating the causes behind crime spikes and shifts. Now that we have established the importance of ensuring our data is stationary, let's implement the augmented Dickey-Fuller test to assess stationarity in our daily crime counts. We begin by importing the necessary function from the statsModels library. The add_Fuller function conducts the test, taking our daily crimes data as input and returning multiple values, including the p-value. The p-value is critical because it helps us determine the presence of stationarity in our time series data. A low p-value, typically below 0.05, indicates that we can reject the null hypothesis of non-stationarity. By printing the p-value, we can easily assess the stationarity of our dataset, laying the groundwork for fitting an AIMA model. Assuming our data proves stationary, we will now fit an AIMA model to make predictions. We start by importing the AIMA class, followed by defining our model parameters, which represent the autoregressive, differencing, and moving average components. After fitting the model to our daily crime data using the fit method, we can make forecasts for the next 30 days. This predictive capability is crucial for law enforcement agencies, as it aids in resource allocation and planning based on anticipated crime trends. Now let's implement the following code to detect anomalies in our daily crime data using the interquartile range (IQR) method. First, we calculate the first and third quartiles labeled Q1 and Q3, which represent the 25th and 75th percentiles of the dataset, respectively. The IQR is then determined by subtracting Q1 from Q3, which gives us the range within which most data points should fall under normal circumstances. Next, we define the boundaries for what we consider as normal data points. Specifically, we calculate the lower bound by subtracting 1.5 times the IQR from Q1, and the upper bound by adding 1.5 times the IQR to Q3. This effectively sets the limits beyond which any data points can be viewed as potential anomalies. Finally, we identify these anomalies by filtering our daily crimes data. Any crime counts that lie outside of our established lower and upper bounds are flagged as anomalies. This method allows law enforcement to focus on unusual crime spikes, which could indicate significant events or trends. The results of this analysis will help in understanding and responding effectively to emerging patterns in crime data. Time series analysis extends beyond crime statistics, finding applications in diverse fields such as finance, healthcare, marketing, and urban planning. For instance, financial analysts use time series analysis to predict stock prices, evaluate market trends, and assess economic indicators. In healthcare, analyzing patient records over time can identify public health trends or seasonal outbreaks. Marketing professionals use time series data to optimize advertising campaigns by evaluating past consumer behavior and deriving insights from purchasing trends over time. By analyzing sales data over specific periods, businesses can better forecast demand and adjust inventories accordingly. Urban planners analyze traffic patterns to make informed decisions about road expansions and public transportation systems. Each of these applications showcases the versatility of time series analysis as a methodology for drawing critical insights from temporal data, allowing stakeholders to make informed, data-driven decisions. As we approach the conclusion of this tutorial, let's recap the main applications of time series analysis we covered today. We explored how to visualize crime data to understand trends over time, applied decomposition techniques to separate trends and seasonality, fitted AIMA models for forecasting outcomes, and detected anomalies using the IQR method. These techniques enable us to extract actionable insights from temporal datasets, showcasing the immense value embedded within timestamped information. The Denver crime dataset serves as an excellent example of how time series analysis frameworks empower us to understand complex patterns and behaviors, ultimately leading to enhanced decision-making in various sectors. Time series analysis is not merely an academic exercise. It's a practical toolkit that empowers us to navigate the ups and downs of real-world data. Whether you're delving into crime statistics or exploring market dynamics, mastering the art of time series analysis can transform how you comprehend and respond to your data-driven challenges. Embrace the journey of exploring time series analysis and let its insights guide your analytical practices moving forward. Happy analyzing. Now let's take a look at how we can create a pandas data frame to demonstrate the impact of using the object data type for storing strings. In this example, we first import the pandas library, which is essential for data manipulation and analysis in Python. We then define a simple dictionary containing city names as strings and their respective populations as integers. This dictionary forms the basis of our data frame. Next, we initialize the data frame using the DataFrame function, which converts our dictionary into a structured format that allows for easy data manipulation. Once the data frame is created, we can examine the data types of its columns by using the dtypes attribute. This will reveal that the city column, where we stored our city names, is represented as an object data type. This is crucial because, as discussed earlier, using object dtype can lead to inefficiencies in memory usage and performance, particularly when working with larger data sets. By running this code, we emphasize the importance of recognizing the data types we use and their implications for data handling in pandas. Next, we will write the following code to filter out cities that contain the letter O using the str_contains method. This function allows us to work with string data efficiently. By applying it to the city column, we create a new data frame that only includes rows where the city name contains the specified letter. This illustrates how string manipulations can be performed in pandas, but it's essential to recognize that since city is still an object D-type, this operation may have performance implications. Now let's implement the following code to convert the city column to a categorical data type using the astype method. By transforming city into a category, we are carving out an optimized structure that reduces memory usage and enhances overall performance for string operations. After executing this code, we can check the data types to confirm that city has successfully changed from an object type to a categorical type. This shift not only supports faster filtering and grouping, but also ensures the integrity of our data manipulation efforts as we continue to work with our dataset. Now let's take a look at how inconsistent data types can introduce errors in our analysis, specifically when working with string operations in pandas. We begin by creating a dictionary called DataInconsistent, which contains a city column with mixed types, including a numeric value, and a population column where one entry is a string indicating, not a number. Next, we build a data frame DF_inconsistent from this dictionary. Here we attempt to filter the data frame to find cities that contain the letter O using the str_contains method. However, because one entry in the city column is a numeric value, pandas will not be able to apply string operations smoothly. Therefore, when we run this filtering operation, we anticipate encountering a type error, which is captured in the try and except block. This demonstrates a key pitfall of using the object data type. Unexpected data can disrupt operations that presume a uniform type. Understanding this risk underscores the importance of cleaning data and ensuring that all entries conform to the expected types before performing such operations. Now let's implement the following code to handle our inconsistent city data effectively. First, we convert all entries in the city column to string format using the astype str method. This step ensures that every value, regardless of its original type, is treated uniformly as a string, thereby minimizing the risk of type-related issues during analysis. After the conversion, we proceed to filter the data frame for cities that contain the letter O using the str_contains method. This method accesses string functions available within pandas, allowing us to perform string operations efficiently. By standardizing the data type, we not only eliminate any potential errors that may arise from mixed types, in this case numbers amidst string entries, but also prepare the data for more streamlined processing down the line. Upon executing the filter, the resulting data frame named filtered cities fixed displays only those cities that meet our criterion. This approach showcases the importance of data cleaning and type consistency in achieving smoother data manipulation and enhanced performance during analysis. Now let's take a look at how we can effectively store zip codes using pandas. We start by creating a list of zip codes, intentionally including a repeated value to showcase the benefits of using categorical data types. By initializing a data frame with this list, we have a structured way to manage our zip code data. Next, we convert the zip code column to a categorical data type using the astype category method. This conversion is key because it optimizes memory usage and enhances computational performance, especially since zip codes have a limited set of possible values that don't change frequently. After this transformation, we can check the data type of the zip code column to confirm it has successfully transitioned to the categorical type. This ensures that operations on this data, such as filtering or grouping, will execute more efficiently compared to if it were stored as an object data type. In scenarios like working with unique identifiers, adopting categorical types can lead to faster computations and less resource consumption, making it an effective choice for handling such data in pandas. Next, we will write the following code to transform the city names in our data frame. By utilizing the str accessor, we can efficiently convert all city names to uppercase. This operation capitalizes each character in the city column, providing a new column called cityUpper which contains the modified names. This method is not only convenient, but also leverages the advantages of using categorical data types, which we set earlier. As we work with a large dataset, maintaining performance is crucial. Hence, this approach ensures we perform string transformations swiftly. After executing this line of code, we can print a subset of our data frame that includes both the original city names and the newly created uppercase city names. This allows us to easily verify that the transformation was successful while also showcasing the efficiency of the data type conversions we applied. It's a simple yet effective way to enhance our data presentation for better readability and analysis. In summary, avoiding the use of dtype equals object to store strings is vital for efficient data handling in pandas. By utilizing categorical data types for non-unique, repeatable data and ensuring all strings are correctly formatted, you can improve performance significantly. Remember, a good practice is to analyze your dataset first, clean it, and choose the right type based on the nature of your data. So there you have it. Whether you're cleaning data, filtering, or manipulating strings, having a strong grasp of data types can be your secret weapon. Let's harness these principles in our upcoming analysis tasks and ensure we handle data the efficient way. As your datasets grow larger, you may find that you have to pick more optimal data types to ensure your data frame can still fit into memory. Memory efficiency is crucial in data analysis and can significantly impact the performance of your applications. Today, we're diving into how to optimize data types in pandas, exploring strategies that help manage memory usage effectively so that you can work seamlessly with even the largest datasets. So far, we learned about the drawbacks of using the object data type in pandas, particularly for storing strings, which can lead to inefficiencies and errors. We explored how employing categorical data types can enhance performance by reducing memory usage and speeding up operations. Additionally, we discussed the importance of cleaning and converting data to ensure uniformity, as well as leveraging pandas' string manipulation functionalities for efficient data handling. These practices are essential for effective data analysis and decision-making. Now, we will cover how to further optimize data types in pandas for memory usage. Now let's take a look at how to create a simple data frame in pandas and inspect its data types and memory usage. The code begins with importing the pandas library, a fundamental step for any data manipulation in Python. We then define a dictionary that encapsulates our data into 3 columns: age, salary, and city. Once we have this data structured, we create the data frame using PD. Data frame data, which allows pandas to automatically infer the appropriate data types for each column based on the values provided. To understand how efficiently our data frame is structured, we check the data types assigned to each column using printdf dtypes. This output helps identify any potential inefficiencies, such as the city column being categorized as an object type, which is less memory efficient. We also examine memory consumption with printdf memory usage deep equals true, providing insights into how pandas is utilizing memory for our data frame. This step is crucial, especially for large datasets, as improper data types can lead to excessive memory usage, underscoring the need for optimization strategies that we will explore next. Now let's implement the following code to convert the city column in our data frame to a categorical data type. This transformation is crucial because it changes how pandas stores the string values associated with city names, efficiently encoding them as integers. By converting to the category type, we leverage memory savings, which is especially important as datasets expand. Next, we will check the data types of all columns in the data frame once more, allowing us to confirm that city has successfully changed to the category type. Additionally, we will print the memory usage of the data frame using the memory usage deep equals true method. This output will provide an overview of how much memory each column consumes, revealing the impact of our conversion. After executing this code segment, you should observe a decrease in memory usage for the data frame, demonstrating the effectiveness of converting repetitively used string values into a more memory-efficient format. Such optimizations are essential practices in data analysis to maintain performance and efficiency while handling larger datasets. Now let's take a look at how we can create a new data frame specifically designed for optimizing integer data types. First, we define a dictionary called DataNumbers, which contains 2 key value pairs, producted and quantity. These lists contain small integers that comfortably fit within the range of np_int8, which is crucial for memory optimization. Next, we use this dictionary to create a data frame named dfNumbers. After initializing the data frame, we focus on memory efficiency by altering the data types of product ID and quantity. By using the restype method, we explicitly change their data types to np_int8. This practice significantly reduces memory consumption compared to using the default np_int64. Finally, we check the memory usage of our optimized data frame with the print function. This output showcases the memory usage before and after the type changes, illustrating how appropriate data types can save resources and improve performance for larger datasets. By implementing these strategies, we enhance the efficiency of our data manipulation and ensure smoother processing in our analyses. Now let's implement the following code to optimize float data types in a new data frame. We start by creating a data frame that contains floating point values representing temperatures and humidity levels. This structure allows us to store the data in a clear and accessible format. However, in order to manage memory more effectively, we will convert these floating point columns from their default, float64 type to float32. This conversion is significant because it reduces the memory consumption for each entry. While float64 provides high precision, many datasets, especially those dealing with normal temperature readings or humidity percentages, do not require such detail. By using a type NP float32, we effectively downsize our data without losing meaningful information. Once we have made this change, we can check the memory usage of the data frame to confirm the savings we've achieved. This optimization technique not only streamlines memory usage, but also enhances computation speed, allowing for more efficient data analysis. Now let's take a look at how we can efficiently load a large dataset with specified data types to optimize memory usage right from the start. In this example, we're utilizing the PD_read_CSV function, which is pivotal for reading CSV files into a pandas data frame. To begin, we create a dictionary called dtype_dict that clearly outlines the desired data types for each column of our dataset. Here we allocate np_int8 to product ID and quantity, which are small integer values that fit comfortably within the range of this type, ensuring minimal memory consumption. The price column is assigned np float32, allowing for sufficient precision while using less memory compared to the default float64. Lastly, we designate the city column as a category type, which is especially beneficial for columns containing repetitive string values, as it enhances performance and reduces memory usage. By passing this dtype_dict to the PD_read_CSV function, pandas correctly interprets the data types during the loading phase. After loading the dataset, we can immediately examine the data frame's structure and memory usage, enabling us to verify that our optimizations were successful and ensuring we're not introducing performance issues for large datasets. Now let's take a look at how we can audit our data frame to ensure we are managing memory usage effectively. The info method in pandas is a valuable tool for this purpose, as it provides a summary of the data frame structure, including the data types, the number of non-null entries per column, and memory consumption. By using the memory usage equals deep argument, we can obtain a more accurate estimate of memory usage, which is especially useful for data frames with object types. Next, we will write the following command to utilize the info method on our large data frame. When we run this command, we'll be able to see at a glance if there are any data types that might be using excess memory, such as large object data types that could be converted to more efficient formats. This step is essential not only for optimizing memory, but also for ensuring the integrity of our analysis as we work with larger datasets. Regularly auditing our data frame while conducting analysis helps highlight potential inefficiencies and enables us to adjust data types proactively. Now let's take a look at how to handle missing data, which is an essential aspect of preparing your datasets for analysis. In the example provided, we create a dictionary containing an age key with a list of ages, some of which are represented as none, indicating missing values. This simulates a common scenario where real-world data might not be complete. Next, we convert this dictionary into a pandas data frame. This transformation allows us to leverage pandas' powerful data manipulation capabilities, making it easier to handle operations on the data. Since some of the ages are none, it's important to address these missing values before performing any numerical analysis. Therefore, we proceed to convert the age column from its default type to float32. This conversion is crucial because floating point types can accommodate none values, which stand for missing data in pandas, avoiding the pitfalls associated with trying to convert to an integer type that cannot represent none. Finally, printing the data types of the data frame reveals that age is now a float, showcasing how with this conversion, we can manage missing values effectively as part of our overall strategy to optimize data types for memory efficiency. To wrap it up, optimizing data types in pandas for memory usage is a crucial skill for any data analyst or scientist dealing with large datasets. By leveraging more efficient types, converting object types to categories, and being mindful of numerical types, you can create streamlined data frames that enhance performance and improve the speed of your analyses. Always remember to audit your data types and be proactive during data loading. Ultimately, maintaining control over memory usage not only empowers you to handle bigger datasets, but also ensures that your analyses run smoothly, saving valuable time and computational resources. So, as you continue to work with pandas, keep these optimization strategies in your toolbox and watch as your data operations become more efficient. Implementing test-driven development in pandas is a great way to ensure your code is robust, efficient, and maintainable. In this tutorial, we're going to explore how to effectively use the testing utilities provided by the pandas library for your data manipulation tasks. So far, we learned about the significance of optimizing data types in pandas to enhance memory efficiency and performance when handling large datasets. We discussed the drawbacks of using the object type for strings and explored converting them to categorical types for better performance. Additionally, we covered optimizing numerical types by choosing appropriate bit width integers and floats to minimize memory usage. Finally, we emphasized the importance of auditing data types regularly and addressing missing values to maintain effective data handling. Now we will cover how to implement test-driven development, or TDD, in pandas, which will help us in writing more reliable data manipulation logic. At its core, test-driven development comprises a simple yet effective cycle. Write a test, watch it fail, implement code to pass the test, and then refactor as needed. Testing in pandas is made more convenient thanks to the PD testing module, which exposes some nifty utilities to validate the behavior of your pandas objects like series and DataFrames. This approach not only helps in catching bugs earlier in your development cycle, but also aids in documenting your code, as your tests serve as a form of documentation themselves. Now let's implement the following code to begin our journey with test-driven development in pandas. First, we'll install the necessary library, pandas, which is essential for data manipulation in Python. Using pip in your terminal, you can easily install it and ensure that we are equipped to handle DataFrames. Next, we will create a function called add_DataFrames that takes two DataFrames as inputs and returns their sum. To validate our implementation, we will use sample DataFrames, df1 and df2, each containing numerical data. We'll also define an expected result DataFrame that represents what we anticipate our output should be after performing the addition operation. To ensure our function works correctly, we employ the assertFrameEqual method from the PD testing module. This function compares the result of our add_DataFrames function against the expected DataFrame. If the actual output deviates from our expectations, an assertion error will be raised, indicating that something went awry. This testing mechanism serves not only to validate correctness, but also establishes a fundamental framework for future, more complex functions and tests. Finally, upon successful validation, we print a confirmation message indicating that our test has passed. Next, we will write the following function to merge two data frames based on a specified column. The merge data frames function utilizes the PD_merge method to attempt the merge operation. However, a common issue arises when the specified column for merging does not exist in one or both of the data frames. To address this, we will create a test function called test_merge_DataFrames that anticipates this error using Python's raises context manager. In this case, we will provide sample data frames that are missing the common column necessary for the merge. By invoking the merge data frames function with an incorrect column name, we expect a key error to be raised. This setup is a key part of test-driven development, as it allows us to confirm that our code has robust error handling. Through this test, we ensure that our function behaves as expected when faced with unexpected input. Once executed, we should see an output confirming that the test passed successfully by raising the expected key error, demonstrating a secure coding practice when manipulating data frames. Now let's take a look at how we can implement a sorting function in pandas that also includes a corresponding test to ensure its accuracy. The sort DataFrame function is designed to sort a given data frame based on a specified column. It uses the sortValues method, which efficiently sorts the rows according to the values in the designated column. To demonstrate its functionality, we create a sample data frame, df, containing two columns A and B populated with integer values. Next, we establish the expected sorted outcome called expectedSorted, which serves as a benchmark to validate our sorting logic. This expected data frame is constructed by sorting the original data frame by the same column. Now let's see how we can implement the test function, test_sortDataFrame. This function invokes our sorting function and checks if the result matches the expected data frame using AssertFrameEqual, which is a useful utility from the PD testing module that ensures both data frames are equal in structure and values. If the assertion passes, it confirms that our sorting implementation works correctly, establishing a reliable foundation for further modifications and enhancements. Now let's implement a function that filters data frame entries based on a specified date. The filterAfterDate function takes three parameters: the data frame to filter, the name of the date column, and the date threshold. It first converts the date column to a datatime format to ensure proper comparisons. The function then returns only those entries that occur on or after the provided date, effectively narrowing down the data based on time. Next, we create a sample data frame with date values and corresponding values to test our function. The expected result is defined, which contains only the entries that meet our filtering criteria. To validate our function's performance, we write the test_filterAfterDate test case. This test calls the filtering function with a specific date, formats the resulting date column for comparison, and uses AssertFrameEqual to check that the output matches the expected data frame. By passing this test, we confirm that our filtering logic works accurately, providing us with confidence in handling time series data as we explore various date inputs. Now let's implement a performance test for our data aggregation method using a large data frame. First, we define the aggregateData function, which takes a data frame as input and returns the sum of the values grouped by the category column. This function is essential as it allows us to analyze data categories effectively. To evaluate the performance of our aggregation, we create a sample data frame named large_df, populated with 1 million random entries for both the category and value columns. Next, we write the testAggregatePerformance function to measure how long the aggregation takes. Inside this function, we capture the start time before invoking the aggregateData function and then record the end time afterward. This will help us understand the efficiency of our operation. Additionally, we include an assertion to ensure that the result is not empty, confirming that the function works as intended. By printing the aggregation time, we gain insights into the execution duration, enabling us to assess and refine our code's performance under realistic conditions. This kind of performance testing is critical, especially as datasets grow larger, ensuring our data processing remains reliable and efficient. Implementing test-driven development in Pandas might seem daunting at first, but as you get comfortable with the tools and techniques, you'll find it enhances both your coding effectiveness and your ability to manage complex data manipulations. Writing tests for your data frame operations not only aids in catching bugs, but also gives you confidence to make changes and enhancements without fear. Remember the mantra of TDD, red, green, refactor. It's a loop that reinforces good coding habits and ensures that your Pandas operations consistently perform as expected. The utility of the PD testing module in Pandas offers you the resources to verify your logic efficiently, so make it a habit to incorporate testing in your data workflows. Thank you for watching this tutorial on implementing test-driven development in Pandas. Keep practicing your coding and testing skills, and soon you'll be writing tests as seamlessly as you're writing data manipulations. Happy coding! NumPy is often hailed as the fundamental package for scientific computing with Python, forming the backbone of data manipulation and analysis in the Python ecosystem. Today, we'll delve deep into the foundational libraries that make working with data in Python both powerful and efficient. So far, we learned about the significance of implementing test-driven development (TDD) in Pandas to ensure robust and efficient code. We explored the testing utilities in the PD testing module and practiced writing tests for various DataFrame operations, including addition, merging, sorting, and filtering by date. We also highlighted the importance of performance testing, especially when working with larger datasets to maintain efficiency in our data processing. Ultimately, TDD not only helps in catching bugs, but also builds confidence in making changes to our data manipulation logic. Now, we will cover some of the foundational libraries that enhance our ability to work with data in Python. Now let's implement the following code to create an array of evenly spaced values between 0 and 1. This is done using the numpy linspace function, which is a powerful tool in NumPy for generating sequences of numbers. In this case, we specify that we want an array containing 10 values. The first parameter, 0, is the starting point of our array, while the second parameter, 1, indicates the ending point. The third parameter, 10, tells NumPy how many values we want in the generated array, all spaced evenly across the specified range. Once we call this function, it returns an array that showcases the distribution of the 10 values between the specified limits. This abstraction provided by NumPy makes it incredibly straightforward to generate numerical data without manually performing calculations or loops. Finally, we use the print function to display the created array, allowing us to visualize the result of our operation. This concise process exemplifies how NumPy simplifies array creation and manipulation, setting the foundation for more complex data handling tasks. Now let's see how we can implement element-wise operations using NumPy. First, we begin by creating two arrays, array1 and array2, using the nparray function. This function initializes a NumPy array, allowing us to carry out mathematical operations on it. In this example, array1 contains the values 1, 2, 3, and array2 contains 4, 5, 6. Once we have our two arrays set up, we can perform addition directly by using the plus operator. This simple operation combines the corresponding elements of both arrays, demonstrating NumPy's broadcasting capabilities. When we execute the addition, the first elements of each array 1 and 4 are summed, giving us 5, the second elements 2 and 5 yield 7, and the third elements 3 and 6 produce 9. Finally, the result is stored in a new variable called result, which we print out. The output displays the combined values as 5, 7, 9, illustrating how effortlessly NumPy enables us to perform complex operations without the need for cumbersome loops. This efficiency not only simplifies the code, but also optimizes performance significantly. Now let's see how we can load our sales data into a pandas DataFrame, which is essential for data manipulation in Python. We start by importing the pandas library, which is commonly abbreviated as PD. This library serves as a powerful tool for handling tabular data, allowing for easy data manipulation and analysis. Next, we'll write the command to read the CSV file containing our sales data. By using the PD read CSV function, we can effortlessly load the data directly into a data frame called df. This function reads the entire CSV file and converts it into a structured format that pandas can work with, making it incredibly convenient. Once the data is loaded, we can utilize df head to preview the first few rows of the data frame. This quick glance allows us to verify that our data has been loaded correctly and gives us insight into its structure. Hence, this one-liner not only streamlines the data loading process, but also sets the stage for us to perform various data manipulations and analyses as we delve deeper into our dataset. Now let's see how we can filter our data frame to focus on specific data points that interest us. In this case, we want to refine our dataset to include only the sales that exceed $100. To do this, we can directly apply a condition on the sales column of our data frame, df. By using the syntax df sales 100, we create a new data frame called filtered data that holds only the rows where the sales value meets our condition. This is a powerful feature of pandas that allows for intuitive data manipulation. No complicated looping or manual filtering is required. After executing this line of code, we can print filtered data to visualize our newly filtered dataset. The output will display only the relevant rows, making it easier to analyze higher sales transactions. This process illustrates how pandas provides a simple yet effective way to interact with data, emphasizing the library's strengths in analysis and the clarity of your data processing workflows. Next, we will write the following code to visualize sales data over time using Matplotlib, a powerful library for creating static, animated, and interactive visualizations in Python. As we assume that our data frame contains the columns date and sales, we can start by calling the plot function from the pyplot module, which allows us to generate line plots easily. In this case, we pass the date column as the x-axis and the sales column as the y-axis, creating a relationship that shows how sales have fluctuated over a specified time period. To enhance the readability of our plot, we will label the x-axis as date and the y-axis as sales using the xlabel and ilabel functions, respectively. Providing a title for our plot is important as it gives context. We will set it to sales over time to clarify what the viewer can expect from the visualization. Finally, calling show will render the plot so that we can see the trends in our sales data clearly. This visualization will help us decode insights that could be missed in the raw data alone. Now let's take a look at how we can calculate the determinant of a matrix using SciPy. First, we import the det function from the scipy-linalg module, which is specifically designed for linear algebra operations. Next, we define a square matrix using NumPy's nparray function. In this example, we create a 2x2 matrix with the values 1, 2, 3, 4, which is important since determinants are only defined for square matrices. Once the matrix is defined, we can calculate its determinant simply by calling the det function and passing our matrix as an argument. The computed determinant is then stored in the variable determinant. By using the formatted print statement, we display the result clearly, allowing us to see the calculated determinant of the matrix in a readable format. This concise approach exemplifies how SciPy simplifies complex mathematical operations, empowering you to perform advanced computations effortlessly while leveraging the foundational capabilities of NumPy. Such interactions between these libraries highlight the efficiency and power of the Python ecosystem for data science. Now let's implement a simple linear regression model using scikit-learn, which is designed to help us analyze relationships within our data. First, we begin by importing the linear regression class from the sklearn linear model module, enabling us to create a linear regression model. Next, we need to establish our dataset. Here we define our independent variable x and dependent variable y using NumPy arrays. The independent variable is a 2D array representing the input features, while the dependent variable is a 1D array containing the target values we aim to predict. After setting up our data, we create an instance of the linear regression model. This object will help us capture the underlying relationship in our data. By calling the fit method on our model with x and y, we allow the model to learn the best fit line through our data points. Once the model is trained, we can use it to make predictions. Here we call the predict method on our model with new input values, enabling us to forecast outcomes based on what the model has learned. Finally, the predictions are printed, providing insights into the expected values for the new data points. In conclusion, we have taken an extensive look at the foundational libraries that elevate Python's capabilities for scientific computing and data analysis. We explored NumPy for efficient array manipulation, pandas for data structures and operations, matplotlib for visualization, SciPy for advanced computations, and scikit-learn for machine learning, all essential tools in any data scientist's toolbox. Utilizing these libraries, you can create powerful data workflows, troubleshoot your code efficiently, and visualize results effectively. The Python ecosystem for data science is indeed robust and continually growing, with these foundational libraries leading the charge. As you continue to experiment with these libraries, remember that their true power lies in how they interact with one another, creating a comprehensive toolkit for tackling data challenges. Embrace the journey ahead as you dive deeper into Python and its vibrant community. Who knows, you might just discover the next groundbreaking insight from your data. Exploratory data analysis, or EDA, is a crucial step in the data analysis process, helping us to understand the intricacies of a dataset we may know little about. EDA helps us uncover patterns, spot anomalies, test hypotheses, and ultimately make sense of our data. Today, we will dive deep into EDA and explore different techniques and visualizations to better understand our data. So far, we've learned about foundational libraries in Python that enhance data manipulation and analysis, starting with NumPy for n-dimensional arrays, pandas for data structures, matplotlib for visualization, SciPy for advanced computing, and scikit-learn for machine learning. Now we will focus on the art of exploratory data analysis, which lays the groundwork for uncovering insights hidden within our data. Now let's see how we can load our dataset and get an initial glimpse of its structure using Python's pandas library. The first line of code imports the pandas library, which provides powerful data structures for data manipulation. Next, we load our dataset from a CSV file using the pd_read_csv function, assigning the resulting data frame to the variable df. This data frame is a two-dimensional, size-mutable, and potentially heterogeneous tabular data structure, ideal for our needs. Once we have loaded the dataset, it's important to understand what it contains, and this is where the head function comes into play. By calling df_head, we display the first 5 rows of the data frame. This provides an immediate overview of the data, allowing us to inspect the columns present and understand the type of data each contains. It's like a quick preview that helps us decide how to proceed with our exploratory data analysis. This foundational step sets the stage for deeper exploration, guiding us to identify any cleaning or transformation needs as we delve further into our dataset. Now let's see how we can check the dimensions and data types of our data frame to better understand its structure. The first line of code retrieves the shape of the data frame, producing a tuple containing the number of rows and columns. By unpacking this tuple into the variables rows and columns, we can conveniently report how many records and features are in our dataset. This information is pivotal as it provides a quick overview of the dataset's complexity and can guide us in identifying potential areas for cleaning or transformation. Next, we implement a command to examine the data types of each column. The dtypes attribute helps us understand the kind of data stored in each feature, distinguishing between integers, floating point numbers, strings, and other types. Knowing the data types is essential for ensuring that we apply the correct methods for analysis and manipulation later on. With these insights, we lay a solid foundation for further exploratory data analysis, enabling us to dive deeper into the nuances of our dataset and prepare for more complex analyses ahead. Now let's see how we can check for missing values within our dataset. Missing values can significantly impact our analysis, so it's vital to identify them early in the exploratory data analysis process. We will use the isNull method, which returns a data frame of the same shape as ours but with Boolean values, true for missing values and false for non-missing values. By chaining this with the sum function, we can quickly obtain the count of missing values in each column. This approach provides us a clear overview of the extent of the missing data, allowing us to decide how to address it. For instance, we may choose to drop rows with missing values, impute them with a default value, or even leave them as is depending on our analysis goals. It's essential to document whatever approach we choose, as it influences the integrity and robustness of our findings. Thus, we assign the result to the variable missing values and print it out, giving us a snapshot of our dataset's completeness and guiding our next steps in data cleaning and preparation. Next, we will examine the descriptive statistics of our dataset to gain insights into its distribution and variability. To achieve this, we'll use the describe function from pandas, which provides a comprehensive statistical summary for all numerical columns in our data frame. When we call describe, it computes essential statistics like count, mean, standard deviation, minimum, maximum, and various percentiles. This summary acts as a cheat sheet for understanding the general behavior of our dataset. By analyzing these statistics, we can efficiently identify trends and outliers that may require further investigation or cleaning. Once we've gathered this information, we print the statistics to visualize them clearly. This step is vital because it equips us with the necessary knowledge to make informed decisions during our analysis, ultimately driving deeper inquiries into any anomalies or patterns we uncover. Understanding these descriptive statistics serves as a cornerstone in our exploratory data analysis, guiding us as we move forward with more advanced techniques and visualizations. Now let's implement the following code to create a histogram that visualizes the distribution of a numerical column within our data frame. This visualization is crucial in exploratory data analysis as it allows us to understand how values are distributed across different intervals. In this code, we begin by importing the matplotlib pyplot library, which provides a flexible framework for plotting. After that, we use the plthist function to plot our histogram. We specifically target the column named numerical column in our data frame df, which we assume contains our numerical data. The bins parameter is set to 30, meaning the data will be divided into 30 equal intervals, allowing for a detailed view of data distribution. We can adjust this number for different visual effects or clarity, depending on the dataset's characteristics. Additionally, we customize the histogram's appearance with parameters like color set to blue and alpha set to 0.7, which adds a degree of transparency. This makes our histogram aesthetically pleasing and improves readability. Finally, we add titles and labels to the axes to clarify what each element represents, making our visualization easier to interpret before calling pltshow to display the histogram. Now let's see how we can implement a scatter plot to explore the relationship between two numerical variables in our dataset. The pltscatter function from the matplotlib library is used to create this visualization, where we specify the two numerical columns from our data frame, numerical column 1 and numerical column 2. Each point on the scatter plot represents an observation from the dataset, providing a visual representation of how these two variables may correlate. To enhance the plot's interpretability, we include a title that succinctly describes what the scatter plot represents, along with labels for both axes. The alpha parameter is set to 0.5, which makes the points semi-transparent. This is particularly useful in dense plots as it helps reveal overlapping points. Finally, the pltshow command generates the scatter plot, allowing us to observe potential clusters, trends, and outliers. This insight is invaluable while performing exploratory data analysis, as it reveals the dynamics between the selected variables and informs further analysis. Now let's see how we can create a bar plot to represent the frequency of categories in a categorical variable. First, we utilize the value counts function on the specified column of our data frame, which counts the occurrences of each unique value within that column. This gives us a clear picture of how many instances of each category exist in our data. Next, we take this frequency data and plot it using the plot method, specifying the kind of plot as bar. We also set the color to orange and adjust the transparency with the alpha parameter to make the bars visually appealing and easier to read. Adding a title with PLT title helps contextualize the information being displayed, while PLT X label and PLT illabel label the axes, indicating what categories and counts the plot represents. Finally, with PLT show, we render the plot to visualize the distribution of categories clearly. This bar plot not only helps identify the most common categories, but also those that might require further investigation due to their low counts, enhancing our exploratory data analysis. Now let's see how we can delve into correlation analysis to uncover relationships between our variables. We begin by importing the Seaborn library, a powerful tool for data visualization. The first line of code computes the correlation matrix of our data frame using the core method, which quantifies the relationships between the numerical features, returning a matrix of correlation coefficients. Next, we move on to visualize this correlation matrix. We use PLT figure to set the figure size, allowing us to create a clear and comprehensible heat map. The SNS heat map function is crucial here. It generates the heat map using the previously computed correlation matrix. The ANOT equals true parameter adds the correlation coefficients to the cells, providing instant insights into the strength and direction of relationships. The CMAP equals coolwarm option enhances visual interpretation by using contrasting colors to represent positive and negative correlations. Finally, we give our visualization a title with PLT title and display it using PLT show. This comprehensive approach not only identifies significant correlations at a glance, but also aids in understanding the overall dynamics among numerical features in your dataset. Now let's take a look at how we can visualize the relationship between a categorical feature and a numerical variable using a box plot. In this code snippet, we utilize the Seaborn library to create a box plot, which offers a clear representation of the distribution of the numerical variable across different categories. The SNS boxplot function is called, where we specify the x-axis to represent the categorical column and the y-axis for the numerical column from our data frame. This allows us to see how the numerical data varies within each category and helps to identify the central tendency, variability, and potential outliers. The plot is further enhanced with titles and labels, improving readability and context. Specifically, we title the plot Box Plot of Numerical Column by Categorical Column, which immediately tells us what to expect. Finally, we use PLT show to display the box plot. This visualization will aid in uncovering insights such as which category shows higher values or if there are significant outliers, thus deepening our understanding of the dataset's dynamics and guiding further explorations. As we conclude our exploration of EDA, it's essential to emphasize that EDA isn't just about the techniques we've covered, it's about the thought process behind analyzing the data. Each visualization, statistic, and hypothesis can lead you to new questions, and as you go deeper into your dataset, your understanding becomes more profound. To summarize what we've covered, we learned how to load and inspect datasets, check for missing values, understand descriptive statistics, and visualize data through various methods like histograms, scatter plots, and box plots. We also discussed how correlation matrices can help identify relationships and how generating hypotheses can lead to richer insights. As you continue your data analysis journey, remember that EDA is the foundation upon which all your insights will be built. By spending time understanding your data through exploration, you set yourself up for success in the latest stages of analysis. Embrace the excitement and curiosity that comes with learning more about your dataset, and who knows, you might just uncover some surprising insights that could change everything. In today's lesson, we are diving into an essential aspect of data analysis, data validation. The adage, garbage in, garbage out, reminds us that even the most sophisticated algorithms can fall short if they are fed poor quality data. So let's ensure our data is pristine before we dive into analysis. So far, we have learned about exploratory data analysis, EDA, and its importance in understanding datasets. We explored foundational techniques such as loading data, checking for missing values, and calculating descriptive statistics. Visualizations like histograms, scatter plots, and correlation matrices were discussed to reveal patterns and relationships within the data. The focus is on utilizing these methods to generate insights that can guide further analysis and decision-making. Now, we will cover how to validate your data to ensure accuracy and relevance in your analyses. Data validation is the process of verifying that the data being used in analysis is accurate, complete, and meets the required standards. Think of it as the quality control step in your data journey. Just like a chef checks ingredients before cooking, data analysts must verify what they are working with. The goal is to ensure your data is free from errors, inconsistencies, and is suitable for the subsequent analytical processes. So how do we accomplish this? Let's break it down into key components, with some practical Python code examples along the way. Now let's see how we can identify and correct data types within our data frame. Initially, we create a data frame with sample data that contains inconsistencies, such as 30 instead of a numeric value for age and not a date in the birthdate column. To assess the current data types, we can utilize the dtypes attribute, which reveals how pandas interprets each column. Next, we will write code to convert the age column to numeric. Using pdtonumeric with the errors equals coerce argument allows us to coerce any non-numeric values to none, facilitating cleaner data processing going forward. Similarly, we can convert the birthdate column using pd to datatime, which also employs the same error handling strategy to manage any invalid date entries effectively. Finally, we will print the corrected data types in the data frame itself to observe the modifications. This procedure not only rectifies inconsistencies, but also helps ensure that subsequent analyses based on this data will yield accurate results, demonstrating the importance of properly managing data types in data validation efforts. Next, we will write the following code to identify and handle missing values within our dataset. The first part utilizes the isNull sum method, which counts and displays the number of missing entries in each column of the data frame, providing us with a clearer understanding of our data's integrity. Once we've identified these missing values, we have two options for addressing them. The first method involves dropping any rows that contain none values by using the dropNA function, which creates a new data frame, dfClean, that excludes these incomplete records. This approach ensures that our analysis is based solely on complete cases but should be applied carefully as it may lead to the loss of potentially valuable data. Alternatively, we can fill in the missing values using the fillNA method. In this example, we replace the missing entries in the age column with the mean age calculated from the existing values, and for the birth date, we use a placeholder date of January 1, 2000. This method, reflected in our df-filled data frame, enables us to maintain the full dataset while still addressing the gaps. The choice between dropping or filling missing values depends on the analytical context and the importance of each row in our dataset. Now let's see how we can validate categorical data to ensure consistency in our analysis. First, we create a data frame called catdf, which contains a column labeled gender with various entries, including some that are not considered valid. Next, we define a list of acceptable values, valid genders, that includes male and female only. This establishes the criteria we will use to check for errors in the data. To validate the entries in the gender column, we apply a lambda function that tests each value against our predefined valid categories. Specifically, the function checks if the value exists within the valid genders list. As a result, we create a new column, genderValid, in our data frame, which holds a Boolean value indicating whether each entry is valid or not. By printing the results, we can clearly see which entries meet our criteria and which ones do not. This approach is crucial in identifying inconsistencies, thereby ensuring that subsequent analyses are not influenced by erroneous or unexpected values. Next, we will write the following code to validate the ages in our dataset by checking if they fit within an acceptable range. We start by creating a dataset with various age values, including some that are outside the realistic human age range of 0 to 120. This step helps us identify potential data quality issues right away. To validate the ages, we define our acceptable range using minimum and maximum thresholds. Now let's implement a method to check each age against these defined limits. We employ the apply function to apply a lambda function that checks if each age fulfills the condition of being between the minimum and maximum values. This results in a new column in our data frame that flags each age entry as valid or invalid based on our criteria. Finally, we print the validation results, allowing us to easily spot any entries that need attention or correction. Through this process, we ensure the integrity of our age data, reinforcing the importance of validations in maintaining high-quality datasets. Now let's see how we can implement format validation using regular expressions, regex, to ensure that email addresses conform to a specific pattern. We begin by creating a sample data frame containing various email entries, some of which may not follow proper formatting. This will allow us to demonstrate our validation technique effectively. Next, we define a regex pattern that outlines the criteria for valid email addresses. This pattern checks for various components, such as the presence of a username followed by the @ symbol, a domain name, and a top-level domain with at least 2 characters. The regex acts as a rule set for what constitutes a legitimate email format. Now let's validate the email formats by applying our regex pattern to each email entry in the data frame. We use the apply method along with a lambda function that utilizes rematch to check each email against our defined pattern. The result is stored in a new column called emailValid, which indicates whether each email address is valid or not. Finally, we print out the data frame to visualize the validation results and easily identify which entries are correctly formatted and which are not. This step is crucial for data integrity, as improper emails can lead to issues later in the data analysis process. Next, let's implement a function called validateData, which will serve as a comprehensive check for our data frame. This function begins by validating data types. For instance, it converts the age column to a numeric format, ensuring that any non-numeric values are coerced into none, thus preventing errors in subsequent analyses. Similarly, it converts birthdate entries to a datatime format, again handling any errors by replacing them with NUT. After addressing data types, the function then checks for missing values by utilizing the isNull_sum method. This step is crucial as it highlights any gaps in the data that could compromise the integrity of our analyses. Following this, we validate the range of the age column to ensure all values lie between 0 and 120, applying logical checks that return a Boolean series indicating the validity of each entry. Finally, we examine the gender column to confirm that all entries belong to our predefined categories, male and female. The function ultimately compiles these results, returning the counts of missing values alongside the validation status of ages and genders. This encapsulation provides an efficient, reusable method that can be integrated into any data ingestion pipeline to ensure consistent quality checks across all datasets. By understanding the importance of validation, you can vastly improve the integrity of your analyses and the accuracy of your insights. In the world of data, every inch of diligence in validation provides you with a mile's worth of clarity in analysis. Paying attention to the finer details while validating data saves you from the glaring pitfalls of poor quality data influencing your results. As you move forward in your data journey, know that engaging in vigilant data validation is not merely a best practice. It's a necessity in ensuring your analytical endeavors stand on a solid foundation. To wrap up today's lesson, data validation is essential for maintaining the integrity, accuracy, and relevance of your datasets, allowing you to make informed decisions based on sound data. We discussed various methods for ensuring data quality, including checking data types, missing values, consistency, ranges, and formats. Remember, validating your data is an ongoing process crucial for the success of any analytics project. Engage thoroughly in each validation step and expect more accurate and meaningful results in your analysis journey.